Imagine being the best of the best. Someone companies, employers, and clients can rely on. Someone that other people come to for advice and technical knowledge. You have mastery, authority, and autonomy. You're a senior engineer who can design complex systems, make smart decisions for billion-dollar companies. Do you have that confidence now? You will after this course. Welcome to Master the Coding Interview System Design. Hold on a second though. This isn't about just acing another boring tech interview. Sure, you're going to ace the interview after the course, but you're not going to do it like most courses and books out there, where you blindly repeat what you read and see and memorize system design. No, we will teach you to think like a system design engineer so you can actually be placed inside a company and feel confident that you can design and architect an efficient, reliable, scalable, and secure system no matter what the requirements, because you know the why and the principles. This course teaches you to be smart, a problem solver, and a thinker, not a follower. If you want to advance your career and stand out from thousands of others that are just reading blog posts and watching YouTube videos, well then maybe you should take this course. I guarantee there's nothing like it out there. It's time to learn the insider knowledge that top engineers with years of experience already know. You're going to learn to design, architect, and build applications from the ground up, no matter the size. Ready to be at the top of the field? Let's dive in.
Hello everyone and welcome to System Design 101. Before we begin, I want to give a quick introduction about what this course is going to be, the format of the course itself, as well as some of the different important things that you want to keep in mind in order to get the most out of this course. Now, many of you have heard of system design. It is something that all engineers need to know, especially as they become senior and senior plus. And more importantly, many of you might be here because you've heard about the system design interview in the FANG interview process. There are some things that I want to mention, though, about the FANG interview specifically, especially if you're here trying to prepare for the system design interview. Now, this is not meant to be discouraging, but it is meant to be realistic, and it's meant to help you be most aptly equipped for the actual interview itself in a realistic way. The interview is notorious for being hard. The difficulty is high, and the reason for this is because system design is the true measure of the experience that you have. Many of the interviews that you do, you can kind of get away with learning about it in isolation or in a vacuum. What I mean by this is that when you do a coding interview or when you do one of the technical data structure algorithm type questions in the interview, you can practice them in isolation to some degree. Of course, experience helps, but generally speaking, they can be learned without a lot of work experience. System design is not that exact thing. System design is the truest measure of what project you've worked on, what architectures you've worked on, what scalability issues you've seen and solved from a high-level architecture standpoint, and it truly is designed to draw upon what your experience is. These interviewers that you have are some of the most experienced engineers, especially when it comes to system design, because they work on some of the largest, most reliable, and scaled out systems in the industry. These tech companies are some of the biggest tech companies, and a lot of what we know about system design has been reinforced by these exact companies. So this is a very important thing to keep in mind. You probably cannot trick them by a lack of experience. The good thing, though, is that this interview does not occur unless you're applying for more senior roles. Often, it's pretty much senior and above that actually provide a system design interview. Most smaller roles or smaller companies will not have it because they aren't facing the kind of problems that these big companies have, and they need to gauge whether you have the experience for, especially in a senior position. So this is one thing to keep in mind. But again, the main thing about the system design interview, and even just general system design, is that it's meant to be a synthesis of the experience that you've had designing systems at scale that are reliable and consistent. So what this course is aimed to do is it's aimed to provide you a 101 framework of how you should understand web architecture, the different pieces inside of it, which you can see here in a diagram. But mainly it's meant to give you a high-level idea of what you need to hold on to in terms of principles so that you know that when you're building and gaining this experience in the industry, how you can take it, synthesize it, and understand the questions to ask, the answers you're looking for, how to guide your thinking when designing systems so that when you actually need to do these interviews or you need to have conversations about system design, that you're in the best place possible to tackle the topic and understand what you're doing. Because from senior positions and above, much of your role is going to revolve around making the best decision you can in the context of the problem you're solving, but in the larger system as a whole. And it's always this architecture and system design topic. So again, this is a 101. It's not meant to be a best prep for the interview, but rather it's meant more so to be a framework or a map for you that when you start reading articles about how other people have solved large system design problems or specific system design problems within their space, you understand what they're trying to achieve and you can get the most out of that information. Because the best way for you to prepare for making better system design decisions yourself is to actually read a lot of things about system design. And throughout the course, I am going to sprinkle in a lot of different key articles that I found extremely interesting about different topics in system design. And as you go through the course and as you read these articles, I'm hoping that you'll get a better idea holistically of system design as a topic. The first thing we're going to do is we're going to go through this map one by one to understand what all these components are. Chances are, if you've worked as a software engineer, whether it be on the front end, the back end, the full stack, you'll have encountered a lot of these pieces before, except now we're going to dive into it from the perspective of high-level web architecture. So now that that's out of the way, let's dive in together. I'll see you in the next video. Welcome back, everyone. So in this upcoming series of videos, what we are going to discuss at a high level is what are these actual systems that we're designing in the first place. Before we even start digging into the nitty-gritty of how you make the actual decisions when it comes to designing a specific system, we need to understand at a high level what is these systems and what are the environments that they live in. With our particular case, we're always talking about the internet, and we're talking specifically about building web applications. So knowing that, let's take a dive into a high-level diagram that I've made for you of what a system mostly comprises of. You can, of course, dive deep into these, and then these different pieces will get much more complicated. But right now, I'm taking a high-level snapshot of this, and we're going to dive into each piece so that we understand and level set what it is that we're talking about when it comes to using a web application, as well as loading a web application, and then what it takes for that web application to actually run properly. I'm mostly going to talk about an application that I believe everyone is familiar with, which is Facebook. So if you're unfamiliar with Facebook, you can just go to facebook.com, sign up, and you'll get a general idea of how that application works. In many different applications that exist on the web, if you take a high-level snapshot of how the system is designed, it's probably very similar to how Facebook is designed. The decisions and the trade-offs that they make inside is more nuanced, and that's where the actual differences are going to be. But for our particular case, this diagram is good enough, and in the context of Facebook, we're going to do a deep dive. Now, there's a lot of pieces that you see here, and for now, a lot of them might not make any sense at all. So that's perfectly fine. We will go into each of them individually. For now, I want to focus on the one that we're all familiar with, which is the browser client. Now, a browser client is pretty much this thing that you interact with every single day. You're interacting with it right now watching this video. What is a browser or a client? When you think about the different devices that you have, whether it be a desktop or a laptop, a phone, a tablet, or any kind of device like a smartwatch, you have these different things that you use on them, which you call applications. And a browser is a very specific kind of application. Something like Google Chrome that we are all very familiar with is a browser application. This browser allows you to interact with the web and access different websites. These different websites most of the time are also web applications. On a phone, you might have a very similar app called Safari, for example, if you ever use an iPhone. And this, just like Chrome, is a browser application. You can also access the web the same way you can with Chrome. You can access Facebook.com and get the Facebook website or web application. A client, on the other hand, you could see as something more direct. So, similar with an iPhone or with a tablet, you can download the Facebook application. By downloading the Facebook application, you can access Facebook directly without having to go through a browser application like Safari or Chrome or Firefox or Opera or any of the other browsers. With the Facebook application, you can just access the Facebook app directly. And this you can call a client. Similarly, on this smartwatch, I have just a plethora of different applications that allow you to access different web applications, or you can access directly through different browser applications. It's just meant to capture the same idea, just a different device. So now that we understand what is a browser and a client, what is it that it does whenever you utilize this browser client? So let's take Chrome as our example. We've all seen this screen before whenever we use Chrome or any browser. Up here, you type in the URL of the website you're trying to access. So here, let's say you type in www.facebook.com. When you hit enter, what happens is that if you have a stable internet connection, you will now access the Facebook website or web app. Here, what is happening when this happens? We take this for granted because we do this every day. Now, many of you may already know the answers, but let's dive a little deeper into this to get a better understanding. When your browser client wants to access www.facebook.com, what you are doing is you are making a request for the files that help you actually build out the facebook.com website. Your browser does not have these files natively, because if it did, think about the billions, if not trillions of different websites that exist. Your browser doesn't have access to all the files in order to build any of them. Your browser has to make a request for the appropriate files in order to build the website that you're accessing. So where does this request go? Well, if you were to simplify it, where it's going is actually a server, which is a physical device somewhere in the world that's connected to the internet that holds all of those files that allow you to build this said website. So here, if you're trying to build Facebook.com, you're going to be accessing a Facebook server that has the files to build the Facebook website. And when the server receives your specific request from your browser, it will then send back a response with the appropriate JavaScript, HTML, and CSS files that your browser needs to use in order to actually build the Facebook website. So that is really all that's happening. It's pretty much just a browser client that is making a call or a request to a server, and then that server is sending back a response with the appropriate files or data that the browser needs to build said website. This is pretty much all it really boils down to at a very simplistic level. The problem here is that this does not really scale well when it comes to the billions of users in the world accessing the billions of websites. Even Facebook is getting billions of requests every single day to run its application. This is where you have to introduce some more pieces in the diagram. So we've discussed the browser client and we've discussed the server. We'll talk about the server in more detail later, but here what I'm showing you is a basic snapshot of that bigger diagram we saw earlier in this video. But here we're still focused on what is happening when you make a request for a website. So now that we're taking a look at this piece of it, we're going to discuss more of the different portions here in the upcoming video. So now that we understand what a browser client is, let's talk about the next piece in the next video. Welcome back, everyone. So as discussed in the last video, we want to talk about another portion of this particular part of the diagram. So the portion I want to talk about is the communication layer between the browser client and the DNS. So what is the DNS? Well, here you can see DNS is actually an abbreviation of a domain name system. So what is domain name? Well, when you think about the URL that you access, particularly in our example, facebook.com, what you are trying to access is a unique name that is actually something that is human readable, meaning that facebook.com means something to you, but to the computer, it doesn't really mean anything. What facebook.com actually maps to is something known as an IP address. And an IP address is something that the computer recognizes as a unique address somewhere on the web. So the reason why this happens is because if you think about addresses, they're all unique. The address of your home, the address of your office, the address of your parents' home, these are all ideally unique addresses that are not replicated. Because for mail to be sent to these addresses, they must be unique so that people don't receive the wrong mail. Similarly, when you're making a browser request for a website, it's very similar. What you're doing is you're saying, hey, DNS, I have this website I want to access. Can you tell me what the unique address of that is? So when you say, hey, where does facebook.com go? The DNS will actually say, oh, this actually maps to a IP address of this particular 31.1.13.71.6 that I'm pointing to. Now, the interesting thing is that many different companies that own websites, especially big ones like Facebook, they actually have hundreds of thousands, if not millions of IP addresses. And the reason for this is because there are numerous potential servers in the world that can house all the different files to help build out Facebook. And we'll talk about that more later, but just understand that a website doesn't necessarily need one specific IP address. They, in fact, most likely own many IP addresses, but each of these addresses are unique. But here's the thing about the DNS and Facebook having hundreds of thousands or millions of different IP addresses that all pretty much aim to do one thing, which is give the end user the appropriate files to access facebook.com. You as a user, you don't care about what the actual IP address is. All you know is that when you send over facebook.com, you get back the appropriate IP address that will allow you to access facebook.com servers. In this particular case, the DNS is the one that actually helps figure out, hey, you're giving me facebook.com. I'm going to figure out what specific IP address you need in order to actually get what you want, which is access to the Facebook server so you can get the Facebook files. Now here, what you're looking at is actually a specific format of this IP address. I've mentioned before that it's pretty much in this format of these numbers with these dots in between. Now this is the IPv4. So it's pretty much the version 4 of the Internet Protocol, which is what IP stands for. This one pretty much has 4.29 times 10 to the 9 amount of bits. Now why this is important? When the World Wide Web was first created, they didn't really know how many different unique domains or IP addresses they would need to store, because at the first time, no one knew what the internet was going to be. But over time, as we know now, there are so many different websites, and all of them have unique IP addresses. And in fact, they might even have multiple, as we've come to discuss already. What had to happen is that we needed to create a new protocol, which is IPv6. This one looks much more complicated. It can fit way more characters. And because it can fit way more characters, it really significantly increases the amount of capacity or a number of these different combinations that can exist. So here, 3.4 times 10 to the power of 38, significantly larger. And this particular case here, IPv4 and IPv6, the DNS actually has to maintain both of them. Now, do you need to do anything with the DNS in your system design? No, but it's good enough for you to know what is actually happening with the actual domain name system. But this is pretty much it. The DNS, again, once again, you pass it a human readable, unique address, facebook.com, and the DNS will give you back the appropriate IP address. Now, you might be wondering, if there's IPv4 and IPv6, how do we know which version to get back? Well, this is where in the request itself, it's often going to actually have the specific format that it wants back. Now, this might be the browser or this might be the actual request sender itself. In this particular case, say, hey, give me the IPv4 version of Facebook.com. Then we'll get back the list in the IPv4 version. If we say, hey, give me the IPv6 version, then the DNS will give you back the corresponding IPv6, whichever one is inside, and it figures out based on your location and all these different factors which one you actually need to receive. Again, the DNS is the thing that helps handle all of that for you. So with this understood, we can now understand these two pieces, the DNS and the browser client in this diagram. Now, what I want you to see here is that you can kind of start to draw a line between the browser client, the DNS, and then the CDN, which we'll learn later. For now, it's not as important, but you can draw a line on this left-hand side from this right-hand side. And the reason why is because on this right-hand side is where we're going to start talking about the actual application owner's system. So here we're talking about system design. In this particular case, we're going to discuss in the context of Facebook system. Now, again, we're still learning at a high level what all of these things represent in all systems, but it's easier with an example in order to nail down our understanding. So here again, we're using Facebook as the example, and this line that I'm drawing is so that we can know that we're going to start venturing into understanding the system on the side of the application that we're building or we're consuming, which is Facebook.com. So now that we understand this, in the next video, let's start talking about load balancers and web servers. I'll see you in the next video. Welcome back. So in this video, let's discuss more of this diagram that we see here. So first of all, I want to talk about the CDN at a later point. It's not really important right now because we need to understand more of what's happening with these other pieces before we can understand what a CDN actually does. So let's remove that from the picture. Next, what we need to discuss is, well, we've already talked about the DNS, so I'm also going to remove that. So what we're left with is the browser client, the load balancer, and the web servers. But in order to understand what a load balancer does, we need to better understand the client communication with the web server. So we're going to focus specifically on this communication here. In order to understand this, we need to think back to our original example that we learned in an earlier lesson, when we were trying to access the Facebook server in order to access Facebook.com. So when we made this request, remember that here what you're communicating to is something that before I called a Facebook server, but really you can pretty much think of it as a web server or as an application server. It's interchangeable roughly. Essentially all it is that it is just some server somewhere that takes some request about a web application, and then it sends back the appropriate files to the client that it then uses to either build the whole website or maybe build out a portion of the website. Now, why do I say out a portion? Well, let's take the example of Facebook.com again. When we have learned about accessing the Facebook website the first time, we typed in Facebook.com and we got back the entire website, meaning we got back all of the files required for us to load the initial page. Now, if you've built any kind of web application before, you're very familiar with what's happening here. If we narrow down instead of not the whole application, but a specific feature on Facebook.com, specifically the newsfeed, what's happening here in the newsfeed? Well, the newsfeed has a bunch of posts on it. These posts, as you know, with Facebook newsfeed, is updates from friends. Maybe they're different articles from these different newspapers or magazines that you're subscribed to. Maybe they're updates from different groups that you're signed up to. The main idea here is that these posts are most likely chronologically ordered based on when these different posts themselves were created. So as you navigate through this newsfeed, you should see different posts, most likely in chronological order from the newest to the oldest. Now, let's block out everything else and let's just hyper-focus on this newsfeed, because here we're going to understand more about what a web server is doing. When you think about the actual newsfeed itself, what's happening is that when you first land on the website, let's say for simplicity's sake, we have two different posts. These are the latest posts that are relevant to us, our specific user, so your specific profile. Here, what you do is you see the two, and you're like, okay, maybe I've read them, maybe I don't care about them. As you scroll down, what happens is Facebook will then load you 2 more posts. Again, you might look at them, you might be interested, you might not be. You scroll again, and Facebook will once again load you 2 more posts. And this goes on and on and on until you have no more posts left, which, let's be frank, never happens. What's happening behind the scenes here is that your specific user, let's say I'm user 1, I am requesting posts to a web server because the web server has to give me the data for these posts. Again, on my browser or my client, I don't have all of this data. I don't know. My phone or my computer or my browser has no idea what it needs in order to figure out what the latest posts are. A web server is figuring that stuff out. My client is the one that's sending the request for more post data to the web server. And then this web server is sending that post data back. Most likely, this data is in the format of JSON. So this web server sends it back as a response, and then my client will use that JSON to build in the new posts that I want to see. So if I keep scrolling, as we saw in our previous example, chances are what's happening is I'm actually sending another request to the web server, and then the web server is sending me the appropriate posts JSON. So this is a cycle that keeps going whenever I need new posts. Now, in order for us to understand more about what a web server specifically is, we need to understand this in the context of being able to deliver some specific functionality or purpose, such as the appropriate posts for the appropriate user. The core things that make a web server work is pretty much something that allows a web server to run application logic and a database. Now, what is application logic? Application logic is pretty much the low-level code that you write on the day-to-day as a developer. Maybe this is the JavaScript code you write, the Ruby code you write, the Java code you write, maybe the Carbon code you write. All of that code that you are writing as a developer serves some kind of application logical purpose. You're trying to derive some kind of outcome, maybe a combination of multiple outcomes, but there are a sequence of steps that a computer can understand. And the computer in this case is the web server. This application logic is trying to apply some type of transformation steps on some specific data. In our particular case with the posts, it's all of the post data. Now, all this post data has to live somewhere. It most likely lives inside of a database. The database is solely meant to hold data in specific categories. In our particular case, all of the post data probably lives in a post-related database. The application logic will then sift through all of that data to find the appropriate posts to send back for a specific user. There may be billions of post data, maybe trillions of post data, and the application logic has to figure out within those billions to find the 2 that user wants to see right now. So that is the 2 combination of things that drives a web server. Now, when you think about the web server, we're talking about right now just one user client trying to ask the web server for posts related to user 1. But you can imagine with an application like Facebook that there are hundreds, if not thousands, if not tens of thousands, even millions of users all trying to access that web server to get the relevant post for them. So this is something that is constantly happening, which is putting our system under an enormous amount of traffic and an enormous amount of strain. Now, in order for the web server to function and run that application logic, it needs to actually consume resources. To do that, it's not free. Now, if you've ever built a computer before or worked with a computer before, you know what these resources are. It's pretty much some kind of storage, some type of memory, some type of processing power, and then some kind of network. Now, storage in this particular case, you can think about as like your hard drive on a computer. On the laptop or the PC that you're running right now, you have a hard drive. On this hard drive is some memory that it can use to store long-term memory. RAM here, when we talk about memory, is pretty much short-term memory. And this is what your computer needs in order to actually store some temporary but quickly accessible data that allows the applications to run smoothly. Processing power is the actual CPU unit inside of your computer that allows you to run logical programs. So application logic runs on a CPU. And then network speed, well, network speed is pretty much just the access to the actual internet and how fast that access is. So these 4 things comprise of the main resources inside of a web server that are being used in order to perform that specific logic that we're doing. So in our particular case, we're serving up posts. These are the 4 different resources that are used for the web server to do this efficiently for the millions of users. Now, with a web server, when you think about it, the more traffic there is, the more these resources are being consumed in order to do so. So how do you actually increase the capacity for your web server to do this? Well, this is where we talk about different types of scaling, and there's 2 main types. There's vertical and there's horizontal. So let's first talk about vertical scaling. Vertical scaling is where you have your web server and you're saying, hey, I need more resources in order to serve more users and more requests. How do I do that? I'm just going to vertically scale, meaning I'm going to increase these different resources on this one server. If I need more storage, I'm going to add more hard disks. I'm going to increase the amount of storage space I have. If I need more memory, then I'm going to add more RAM chips. If I need more processing power, I'm going to increase the power of my CPU. If I need more network speed, I'm going to increase the network speed on this specific server. The key idea here is that you are just increasing the resources available on this one specific server. This is actually different from horizontal scaling. Horizontal scaling means that what you're going to do is you are going to duplicate or clone the actual web server. So here, each server has maybe the exact same amount of storage, memory, processing power, and network speed. But what you're doing is you are cloning this server multiple times. And you can be cloning these virtually. And that is what we're going to talk about. We're going to talk about what this kind of virtual cloning actually represents. Because right now, it's probably a little confusing. Vertical scaling is really obvious. With your computer, if you've ever built a desktop before, if you want more memory, you can just add more RAM chips. We've done that kind of upgrade before. With web servers, it's not necessarily the same. You can actually horizontally scale through cloning, which you can't do with your physical computer the way that you probably have before, unless you've specifically done this exact action. So that's what we're going to talk about in the next video. We're going to discuss horizontal scaling. Welcome back, everyone. So we're talking about horizontal scaling, and we're talking about cloning these web servers. So what does that mean to clone the web server? Well, let's go back to that example where we understood what comprised of a web server. A web server runs some application logic, and it has access to a database. In this particular case, you can see that the application logic lives on the web server. Now, the database typically lives external to the web server as far as we're concerned, because the web server communicates with the database in order to get this data. But let's talk about cloning out your web server. You are going to clone the application logic because the logic runs independent of the server. It doesn't really care what server it's running on. The code stays the same. However, does it make sense to duplicate the data in the database if it's pretty much the same data? Probably not. The database should pretty much just contain all of the data, and then all these different web server copies are all going to connect to the same database, and then the respective application logic will sift through the database data to pull out the appropriate things it needs in order to serve its appropriate function. So this is cloning. You're essentially just duplicating these web servers, most likely virtually, just meaning that you're copy and pasting these web server nodes, which we'll talk about more later. For now, all you need to understand is that they're duplicates of the application logic. And then chances are with a database, they're all just accessing the same database somewhere on the system in order to serve the actual code function that it has to do. So now that we understand, at least at a very high level concept of this cloning as an idea of scaling out the system horizontally, how do we now fit this into this model where we have all of these hundreds, if not thousands or hundreds of thousands of users all trying to still request posts from our web server? How do we horizontally scale out these web servers in order to service all these different users? Well, the answer here is to use a load balancer. But before we even explore a load balancer, we need to understand some of the problems that are going to arise and what load balancers do in order to solve these problems. but also there's a couple assumptions we need to understand. So here I'm going to move this out like so. Here what you see on the left is a bunch of different user client browsers. So on the left, I've split it up like this so that you can see it as a really large number of them. On the right-hand side, you see that we've divided into web server A, B, and C. So for all intents and purposes, these three web servers are clones of each other, meaning they're identical. Now, the assumptions we need to make first is that all the requests have the same latency. Now, what is latency? Latency is the time it takes for the browser to fire a request and then get back a response from the server. That total travel time from when the browser starts making the request to when it receives a response is the latency. Now, for all intents and purposes, I'm going to pick an arbitrary number like 20 milliseconds. It really doesn't matter. The key thing here is that any browser making a request to the server and then getting back a response, this will always be 20 milliseconds. Not just the same browser, but all of the different browsers. They all have the same latency. This way, we even out any factors and we can easily better understand this example. The next assumption we need is that all servers have identical resources. So from the storage to the RAM, which is the memory, to the network, all of those resources we saw earlier, I want you to assume that all three of these web servers have the same amount. This way, we can see them as even clones. And by looking at them at even clones is how we can best understand this example. So here, what we want to talk about is when these requests start being made from the browser. Without a load balancer, we have no real way to figure out accurately how to properly manage the actual requests coming in. It's very easy to see where maybe all of these requests are going to one server. The reason why is because nothing is in the middle managing the actual request frequency and the actual load itself. So the load being the number of requests being made. Here, web server A is clearly getting overwhelmed. In another example here, yeah, we've split it a little bit, but clearly web server A is still on fire because it can easily be overloaded by the number of responses. If it gets a disproportionately large number of responses, then automatically we can see how a server can go down because it cannot handle the amount of traffic or load that it is receiving. This is where in comes the load balancer. The load balancer's sole purpose is to evenly distribute the actual load of requests between the servers available. Now again, under our assumptions where latency is the same, then of course we need to evenly split the load. In real life, different requests take different times. As we know, some requests might be larger because you're requesting more data or different data, or the latency might take longer because you have different network speeds, different computer speeds, different resources on your actual device. These are all possibilities. So what happens with a regular load balancer though? Well, again, a load balancer acts as the entry point into the application space or the system. Here, we're not going to communicate directly to the servers. Instead, we're going to communicate from the browser to the load balancer. That's the first thing that we're going to hit. And then the load balancer is going to distribute the actual requests themselves. So here, a very typical strategy for how to actually distribute the load is called round robin. Now, there are numerous ways that we can distribute load, and we'll talk about that later. Right now, that's not important. The main thing you need to understand about how the load balancer chooses what server to route a request to is the strategy. And the round robin strategy is a very common one. All this says is that we're just going to go in order of the list of servers we have access to. So as requests come in, you'll just see that all it does is it goes to the next corresponding server in the list. So if we get a request, server A, then server B, then C, then A, then B, then C, then A, then B, then C, and in that order as long as requests come in. In real life, this might not be the most accurate representation, but what is really happening here is that you are, in theory, getting a really balanced load because our assumption is that the latency is the same between requests, which means that if we evenly distribute these requests, then all these servers should be sharing the load equally, meaning that the load balancer has accurately done what it's supposed to do. Now here, one thing you might notice is that, let's say, for example, we start doing this balancing act. In real life, what happens is that servers might go down. This is a very real possibility of what happens. The load balancer is smart enough to know that if a server goes down, it's not going to route any requests to it. Instead, it's just going to distribute the load with the remaining servers that are up. So this is another thing that the load balancer can do. The whole idea you can think about the load balancer is that it's essentially the traffic cop. It's the thing that knows where to send all the traffic. So it is the one that is responsible for balancing the traffic that's coming in. Load balancers are a very crucial component in system design. In many systems at scale, there are numerous load balancers because, as we see, if we get massive amounts of traffic, which most of these large systems do, then you need to be able to properly distribute this load so that your system is reliable. You want your servers to be evenly receiving the amount of requests so that these servers are not overwhelmed, because that is the whole point, really, of system design. Or at least it's one of the very crucial things that we're trying to maintain. We're trying to manage traffic, which is the whole idea of designing a system so that it's scalable. Of course, you want the system to solve the intended purpose of the application, but more importantly, you want to make sure that this system is robust and reliable. It should not go down from a large amount of traffic. So that's what you're designing around. So the load balancer is a very crucial component that really reflects some of these ideas that we're trying to solve in our system design. Now we're going to continue learning about other functionalities of these load balancers, and we're going to do a much deeper dive later in the course on a load balancer section where we talk about different strategies. But for now, we just need to understand, again, the high level of what these tools are, walking through the architecture of an application in a system. So this is a very general idea of what load balancers do. In the next video, let's keep going. I'll see you there. Welcome back, everyone. In the last video, we started talking about load balancers. We learned how load balancers essentially manage the amount of traffic that each web server receives from the numerous number of browser clients that are making requests to our system. In this video, we're going to talk a little bit more about what else load balancers can do. Now, here I'm going to show you an example where we still have our three clones, web server A, B, and C. But on the left here, I'm reducing the example down to 4 different user clients. The reason for this is because we need to talk about session persistence. What is session persistence? You can think about applications where you need to maintain a consistent connection between your client and your server because you're constantly requesting information. When we think about our Facebook example with the news feed, if you're continually scrolling, or if you have Facebook Messenger open and you're constantly chatting with a different user, in that case, what's happening is that you're constantly making requests to the web server in order to receive new data that is specific to the session you have open. Think about many applications that you use today. You have a persistent session where there's information the web server needs to know about what you're doing so that it can give you up-to-date information relative to your session. This means that this communication between your client and your server has to be consistent, meaning that you cannot jump between multiple servers and one client. The reason for this is because that server is the one that is aware of what it has given the session so far. So this means that you need to maintain some type of persistent connection between a client and a web server. So here, let's take an example and see how the load balancer does this. So very similar to what we saw before, user 1 sends a request to the load balancer because the load balancer represents the entry point to our system. The load balancer, following round robin, will then be like, oh, of the servers I have, which one is the available one? Well, server A is the first one that's available in my list, so I'm going to establish the connection, and then now I'm going to lock it in. So now user 1 can continue to request things from this new server A connection it has. So it will send the request, which the load balancer will pass to server A, because that is now the connection between user 1 client and server A that the load balancer remembers. The load balancer is keeping track of that session persistence, meaning that the session between user 1 and server A is maintained, and the load balancer knows whenever it receives a request from user 1, it's going to forward it to server A because that's the established connection. Server A will then send that response back to the load balancer, and the load balancer will send that to user 1. And this connection continues to be maintained, so when user 2 comes in and says, hey, I'm trying to establish a connection, I want something, the load balancer goes round robin again. Oh, next available server, server B. It's balancing it the same way. It's just going in order. And now, just like we saw before, connection is established. When user 2 requests post, the load balancer knows, oh, this goes to server B. That's what I have stored in my memory. And now when server B sends back, hey, I've got these posts for user 2, the load balancer passes it on. Again, user 3 will do a request to the load balancer. Same thing, load balancer sees, according to my round robin, which is the next server. What's server C? So here now, we establish this connection. I'm keeping this locked in my memory. Now when user 3 requests post, the load balancer passes it to server C. Server C passes back the response, which the load balancer passes back to the correct client, user 3. And then finally, with user 4, we send a connection request to the load balancer. Load balancer goes, oh, round robin, what's my next server? We went through C just now, so we're going to start all over again, back to web server A. Now, it's true that at this point, server A is retaining a connection between user 1 and itself. So here, server A might actually already be getting traffic. But again, the load balancer doesn't need to know that. All it knows is that, hey, I'm assuming that these servers do have capacity and that they are equal according to the round robin strategy. So just like before, this connection gets established. We then make that connection. And now when user 4 requests posts, it knows to pass it to server A, and then server A, when it passes back the response, the load balancer continues to pass it to the correct user. Now here, these connections are now maintained. So no matter how these requests continue to go, the load balancer knows to retain these sessions so that it's always passing the requests and the responses to the appropriate client. And this maintained connection is different from what we saw previously because, again, these servers have context of the sessions. This session persistence is not always necessary, but in certain applications that we need, where there does need to be session persistence, the load balancer is the one that can really help us retain this. Now, the actual strategies for this type of session persistence we'll talk about later in the course when we talk more about load balancers. But for now, just understand this is another function the load balancer can do in a very common setting where we do need session persistence in our applications. So, as we discussed before, what happens if a server goes down? Let's say that we had these sessions and these different connections already maintained and established with our load balancer. What happens, the load balancer now knows that it does need to once again redistribute user 1 and user 4's connections. So here it will have to properly distribute it between server B and server C. Now, the thing here to remember is that in this context, what is happening here is that when the server goes down, the load balancer knows what the available servers are as resources. All it's trying to do is to actually route the traffic evenly. Whether or not the servers are being overwhelmed or not, and we need new servers, i.e. new clones being spun up or not, that's not always the load balancer's responsibility. Sometimes it is, sometimes it isn't. But the key thing to remember here is that at least in this example, we're not focused on that right now. All the load balancer needs to do is just distribute as best as it can the load. Now, for those of you that are curious, how is it that with session persistence, if server A went down, how does server B and server C, who are taking over user 1 and user 4 sessions, keep track of what the session's information was that server A was doing? So here is where there are different strategies of how you actually retain that session information. You can keep it on the client with user 1 and user 4 respectively having information that gets sent in the requests about what the session is about so far. And then server B and server C, when they take over, they'll have to spend some time computing to make sure that they catch up to what server A was doing so that they can accurately take over the session. This is going to happen regardless. There needs to be some additional time that server B and server C need to catch up to the session. That is inevitable. But where you store that information so that they can figure that out, you can do it on the client or you can do it on the load balancer. These are two different strategies. We'll go into them much deeper when we actually, again, talk about load balancers in a greater depth later. But for now, in case you're curious, that is something that does need to happen. If a server goes down and another server needs to take over a session, there will be additional computation time in order for these servers to catch up to what's happening. Now, the user experience is going to be worse because they're going to be waiting for these servers to figure it out. So all they're going to see is a delay. But this is, again, part of system design. We try and make our systems reliable, and also we want them to be robust. But in the end of the day, sometimes these things happen. Servers go down and the user gets a bad experience. But we are trying to minimize the amount that's happening. And that's really the core thing that we're trying to establish here, either with the load balancer or much of our system design that we're doing. So there you go. That's pretty much what we need to understand about load balancers at a high level. So now we can move on and look at the next piece in our diagram. Hello, everyone, and welcome back. So taking a look at our high-level diagram that we saw earlier, we've already covered these 4 topics: DNS, browser client, load balancers, and web servers. In this video, we are going to broaden our scope a little bit and focus on some of the more connections attached to web servers. We are going to primarily look at the connection to a database, and also we are going to look at the connection to the caching service. So that's what we're going to cover in the next few videos. To begin with, we need to understand web servers and databases. Now, we're not going to do a deep dive into the types of databases there are. That we're going to cover in a much later section where we do a deep dive into databases and optimizing databases, what database to choose based on what type of problem you're trying to solve. That is all handled later. This is a much higher level analysis on the relationship between a web server and a database, as well as things when it comes to how to optimize for speed and performance when it comes to the general expectation of how your system should be designed with the database. So let's take a look into how web servers and databases typically communicate at this high level. So we know that web servers house our business logic. Business logic, as I mentioned, is mainly that low-level code you write in the day-to-day as a developer. Whether you're a front-end or a back-end or a full-stack developer, you are writing business logic, the code that has some specific functionality or outcome that you expect. All of that code you write is meant to action on some kind of data in order to provide some type of expected outcome. In our particular case with a database, that data that we are trying to apply our business logic on is stored inside of the database. A database's sole purpose is to store and retrieve data. The only thing here is that this process is typically very time-consuming. When we make our web server or our business logic code retrieve data from a database, a lot of us know that the larger the database gets, if we are starting to have millions, tens, hundreds of millions, or billions of entries in the database, that data collection retrieval is extremely slow. Storage is also quite slow, but typically we don't block our web server business logic from stopping when we want the database to store the data. But there are numerous different optimizations that we can do for databases to make it faster. That, of course, we'll cover later. But the main thing that we need to remember is that the whole idea of storing and retrieving from a database typically ends up being the most latency-heavy step inside of our system, or one of them at the very least. So this is one thing we need to remember. Now, when we think about how our browser client communicates with our web server with this database added to our model now, we can see where the speed really impacts us. So let's look back at our example with Facebook's newsfeed. Looking at the newsfeed, we can see some examples where maybe some kind of optimization might exist. When we look at the posts that we have in our newsfeed, you can typically reduce it down to 2 specific kinds of posts. You have user-specific posts, which are posts that are very unique to you as an individual user. These might be related to your friend group or maybe your specific interests that don't really have a lot of overlap. The thing I want you to remember about user-specific posts is mainly that if you were to imagine all of the users that exist on Facebook, these are the posts that really only are tailored for you specifically. So maybe if you have, let's say, 4 specific friends, how many people are actually connected to those friends? Maybe not a lot, in fact. So maybe out of the billions of users on Facebook, only, let's say, maximum 50 people are going to receive the posts that those friends make. Or maybe that one friend makes, because maybe he doesn't have a lot of friends, you just happen to be one of them. These posts are very specific to you. But then you have things like more region-specific posts. I use the term region because I want you to think about a much larger group of users that receive the same posts. These might have to do with maybe government posts or maybe news posts for your region. Maybe it's even broader than a specific city. In fact, it might be an entire country or maybe an entire continent. For example, let's focus on the North American continent. So maybe all news related to North America, you can imagine that there are a significantly large portion of users, maybe 20-30% of all users on Facebook receive those same specific user posts for that North American region. Now, if we keep that in mind, looking at our example, let's say we look at the North American user 1. This is just the first user in North America, and we're breaking down this model so that we can take a look at an example. Let's say they log onto Facebook and they see their newsfeed, and we're like, hey, I want to request the latest North American posts. Our web server receives this request. It will then apply its business logic in order to figure out what it needs to do to retrieve and get back that data to the North American user. This is where the code that we write, maybe it's Node code, maybe it's Ruby code, it's going to start processing this request, and then it's going to figure out that it needs to retrieve some posts from the database. This might be a combination of some logic it needs to apply as well as database queries. The actual approach doesn't matter. The main thing here is that it needs to interact with the database in order to retrieve these posts somehow. So it goes across that wire and it asks the database. The database's whole purpose is to store and retrieve data, so it will retrieve the appropriate post data and then send it back to the web server. Now, most of the time, this data is not in the shape that the browser client needs. So the web server will further apply some business logic in order to massage it into the appropriate response type. It will then send that back to the browser client, and finally the client gets what it needs. Now this process, as we stepped through and saw, is quite time consuming. You notice how I added the little hourglass to that connection between the web server and the database in order to show that this is pretty time consuming. What you'll notice now is that let's say we have a second user that subsequently makes the same request. They log in and they're like, hey, I want the same thing. I want the latest North American post. We then go through that same process. Web server needs to apply its business logic. But here, what you'll notice is that it's going to go through that exact same arduous, time-consuming step with interacting with the database. But we've already done this before. We're doing the exact same work again. We're repeating ourselves in our system more than one time. Maybe we're doing it for numerous, hundreds of thousands, if not millions of the same North American users accessing the same posts at the same time. This is where we want to introduce something like a caching service. So here, we're going to talk about how a caching service can speed up this process. But that's what we're going to talk about in the next video. For now, I just want you to understand how this process step is necessary because we're doing repeated work, how numerous of the different users, but maybe in the same region, might be making the same interactive call with a database. That's where a caching service most likely is going to enter into the system. So let's talk about that in the next video. I'll see you soon. So inside of our diagram, we looked at how our web servers and our clients and our databases interact with each other. We talked about how that process is rather slow because databases store an enormous amount of data, making the retrieval process much more cumbersome. We talked about how a caching service can help make that faster. And here I want to discuss a bit about the differences between a database and a caching service. Now, they're both two forms of storage. I want to make that clear. A caching service and a database both store data. The difference, though, with a caching service is that a caching service prioritizes speed of retrieval over amount of data stored, where a database stores billions, maybe even hundreds of billions of entries in its data. A caching service stores significantly less. We're talking about hundreds of thousands or maybe low millions. It's definitely designed to store significantly less data. But because it's storing much less data, you're able to retrieve data out of it much, much faster. So in your system design, when you choose to use a caching service, you are doing so with the intention of storing high impact data that you need to pull out fast. Because again, you're not storing a lot of data in it, so you must be storing data into it with a very specific niche or very specific intention. So this is where something like region-specific data that is accessed significantly, much, much more, that is where you want to store it in a caching service. So going back to our example, web servers, again, apply business logic when it comes to the actual performance of what we're trying to get. Databases store and retrieve data. We can even say that it stores and retrieves all of our data. Our caching service caches specific data. So with this in mind, let's go back to our example. We know that we have our first North American user. So at this point, our caching service is empty. The first North American user requests the latest North American posts. Our web server then applies business logic, and it knows that it needs to retrieve these posts from the database because the caching service is empty. So it will go through that process no matter how long it takes. We're trying to retrieve these posts from our database. Our database, of course, knows its function is to store and retrieve this data. It will then retrieve these North American posts, send that back to the web server. The web server then applies more business logic that massages this data into the final format that our clients and browsers need. At this point, before sending it back, what it will do concurrently, meaning at the same time in parallel, it will send those North American posts to the caching service so that it can cache that data. Because now this work has already been completed. Our system, we know, these posts are most likely very high impact given the fact that the region is significantly large. There is a large amount of users that are going to want these posts. We don't want to repeat that work that we just did. So we're going to cache that data, and then the web server is going to send those posts to the browser client at the same time. Once this is done, the next North American user that makes that request for the latest NA posts. Here, the web server, again, has its business logic. And within our business logic is a check to see, hey, can I retrieve these cached NA posts? Meaning, check the caching service to see if these posts that are being asked for have already been cached somewhere. So this request goes to the caching service. And of course, as we know, our caching service does already have these NA posts. And then the caching service will send these posts back to the web server, but it will send a copy. Because again, we might be getting these requests to our caching service hundreds of thousands of times. So our web server will retrieve those NA posts and it will just send that back to the client. And we skipped having to go through that long and latency intensive process of communicating to our database. This is the main benefit of adding a caching service to our system. Now, you can add caching services to numerous steps inside of your system. The main idea with a caching service is that anywhere where you have to send any kind of data that is very labor intensive to do, maybe very latency heavy to do, you add a caching service because it significantly speeds up the amount of work. Caching services are everywhere, and they are very commonly used inside of your system design because interacting with a database is always, generally speaking, quite expensive in terms of time, especially for scaled out and distributed large systems that we're designing. So you will really want to utilize a caching service to speed up that process because outside of reliability, availability and speed is one of the main things you're gunning for inside of your system design. Because now, through adding this caching service, we can see how for every other North American user that follows this one, within, of course, a specific amount of time, as long as that data is still relevant and the one that we want to send to the same group of users, we do not want to repeat that work. We want to just be able to retrieve it quickly from somewhere where we stored that already completed work of caching that data and then send it to every user that is requesting for it. You can see how this might be useful in numerous places in the system. So now that we understand caching, we of course will dive deeper into that as well later on, but you can see at a high level now how caching fits into our big picture of our system design. We've understood databases, we've understood caching services. Now let's continue with understanding more of our diagram. Welcome back, everyone. So now that we've covered some of the more common components inside of a system, let's start taking a look at some of the slightly more advanced topics that we will encounter. Particularly, we're going to talk about job queues and servers. You can kind of break this job queue down into a general queue as well, because that's what we're going to cover. So diving into this, what specifically is a job server and a job queue? So we'll talk about the connection between the job queue and the server a little later, but for now, let's break this term down. What is a job? So jobs are pretty interesting in the sense that they are a very core component of large distributed systems. Here, we're going to understand what a job is in the context of a job server because we've already learned about web servers. So the work here is pretty similar. With web servers, we know that we handle business logic. Now, what is business logic? Well, if we break down business logic is pretty much when the web server has to compute some kind of behavior that the browser client is asking for. In order for us to do this computation, usually we interface with a database, which we've learned about so far. This is where, depending on the context and depending on the developer, the definition of business logic can get a little hazy. Everyone's kind of got a slightly different definition, but one of the most common definitions for business logic is that it is the code that delivers a functionality specific to the business. So when we talk about the business here, we're talking about the actual browser client, so the user. Any kind of logic that drives some type of outcome based on the user's expectations or the user's data or the user's interaction with the actual application, that is all business logic. So any code you write that has to eventually interface directly with the user or as a result of the user, that is business logic. Now, everything else is what we can call application logic. So application logic is still very similar. You're still writing code. It's still driven by the code that you write. It looks very similar to business logic, but the context is not necessarily around the user anymore. So this is just one style of the definition between business logic and application logic. And let's take a look with an example here. So looking at our job servers, let's go back to our Facebook example. Remember when we were looking at our newsfeed? We know that with the newsfeed, we have these posts. But where do we store these posts? In fact, where do we get them from? So I mentioned that we store our post data inside of the database, and then we query for it and we modify it. But how do we make sure that our database has all of the up-to-date posts that a user might query for? So we might get these posts from news outlets, from magazine outlets, or websites particularly, or even blogs. So you can imagine how in Facebook has in its feed a lot of these articles or headlines coming from these external sources, right? These data sources. Here, in order for us to get these up-to-date articles into our database from these data sources, we need some step to do that. This is where the job server can step in and perform that activity. Remember, these sources must be coming into our database at some point throughout the day in order for us to actually provide this to the end user. So here inside of our job servers, we have written application logic or code that will then query these data sources in order to fetch the appropriate news outlets or the appropriate new articles, etc. So you can imagine our job server queries the news and then gets it back, stores in the database, does the same for the magazine, does the same for the blogs. This is pretty much a job. So you can think about a job as a unit of work. It's just some computational work that we need to do in order for our application to actually have the appropriate functionality or the appropriate data that it needs to perform what it needs to do for users. Remember, the user might be able to request from the actual web servers what it needs for it to interact. But as far as making sure we have all of the appropriate data, everything else that might exist inside of our application that is not user-driven, then that is application logic. So here you might be wondering, though, this job equals a unit of work. Unit is a pretty abstract term. What represents a unit? Is a unit of work where we simply query one of our data sources and then update it in the database? Or is it where we query all of our data sources and then update it inside of the database? This is where it gets a little bit more context-driven. It really depends on the amount of work it takes for this to be done. It depends on how much time it takes for this to be done. It depends on whether or not in the process of doing this where things might break. This is where it really depends on the actual context itself. So you essentially need to see jobs in terms of the unit of work as being abstract for this reason. Much of system design is very contextual. It is not just a one-size-fits-all solution for everything. In this particular case, the reason why I wanted to bring up that both of these scenarios could be considered a job is because they can be. It really just depends on the size of the work. And this is where your expertise and your experience, having worked as a senior, is going to benefit you in being able to decide and explain what a job in this case is going to be, because that's what the server is going to do. Now, the reason why I'm hyper-focused on this job being one unit of work is because where we need to now go is to understand, how does this job server know it's time to start running these jobs? This is where we're going to talk about a job queue. And we'll take a deeper look into this idea of a job being a unit of work as well. So the main thing, again, that I want you to remember about these job servers is that there are a lot of these different servers, and there's all this code that actually makes it so that your system does the things it needs to do when it's time for the user-driven code, which is our web servers and our business logic, to actually perform its function. And again, an easy way to think about that with a newsfeed. A user might ask for their specific newsfeed posts, but in order for your application to have the latest posts that all your users might be able to query, that has to be work that is done in the background, independent of the user's interaction. And that you can easily put in the application logic or inside of your job servers. So now that we understand job servers, let's talk about the job queue. I'll see you in the next video. Welcome back, everyone. So in the last video, we talked about jobs being a unit of work and how job servers aim to actually perform these jobs. So jobs being just different types of application work that is done in the background independent of the user's interaction or even the user's knowledge. So we talked about job servers, and we need to talk about job queues. So job queues is essentially a way for us to understand how these job servers know when to perform these job work. So in order for us to understand that, as far as our discussion about what is considered a job goes, in our specific example, I'm going to define a job as our job server reaching out to any single of these data sources, fetching it, and then storing it in the database. So here we can see that going to our single news outlet, this is considered job 1. So a job. Our server requests from the news, and then it updates the database. This news could be any news, BBC, Fox News, CBS. I'm not too familiar with all of the different news outlets, but you can just see them as individual outlets. That is one job. Same thing with any of these magazine outlets. Maybe we reach out to Vogue, and that is considered another separate singular job. Same thing with the blogs. I really don't know any blogs, but you can imagine that reaching out to that one blog and then getting any of the latest posts and then updating it in the database is job 3, another singular job. Now that we've understood what these jobs are, again, the reason why I say they're singular sources is because there can be so many different outlets for news, for magazines, for blogs. There are hundreds of thousands of them. And reaching out to each of them individually is considered one job. I'm not saying reaching out to all of your news is one job. I'm saying in our specific example, just reaching out to one of them and getting the latest posts or the new posts and then storing them in our database, that is considered a job. Now, the job queue. What is a queue? So if you have done data structures and algorithms, you will have learned what a queue is. We have, of course, those courses, and you can take them and learn about queues. So if you're familiar with a queue, you know what it is. But for those of you that are not, let's go over the basics of a queue. A queue is essentially very similar to this concept of a queue in the UK. It's pretty much a line. So you can imagine that there is some kind of bouncer or doorman that is guarding the entrance into some kind of event. When you queue up, you start lining up. People come and line up in front of the queue. And the whole idea here is that the order matters. We want to say that the first person in is going to be the first person out. So the first person that comes is the first person that gets to go in. There is a line here. So the order you can see beneath 1, 2, and 3. And this will be the order in which they go through the line. The order that you arrived is the order that you go through. Very simple here. The only difference now, instead of people, I want you to see these as jobs. So whatever jobs got queued or whatever jobs came first is going to be the jobs that go through to get processed by the job server. So here, of course, with the same order, the news came first and then the magazine and then the blog. So now that will, of course, be the order that they get sent into the job server for the job server to do. Now, that is a basic queue. There is also something called a priority queue. A priority queue instead has 2 rules now. Things come in with a certain priority. This could be just a number that is weighted, so it could just be an increasing order. The higher the priority, you want to prioritize doing that job regardless versus anything of lower priority. And after that, we still follow the first in, first out rule. So here, let's say we have our news. This news that comes in as a job has a P2, a priority of 2. But then there's this magazine that comes in, this magazine job, and it has a P1, so a priority of 1. And then we have the blog come in, and this has a priority of 2. Now here, if we were to follow the steps that we need with our priority queue, what is going to be the first thing that we need to process, the first job? Well, following our rules, what is rule number 1? We want to make sure that we push higher priority more than lower priority. So looking at our 3 jobs, P1 has the highest priority versus anything else. So again, I'm going to say that 1 is greater than 2, greater than 3. So pretty much we'll go by Olympic rules of who wins, right? So first place, second place, third place. So P1 has a higher priority or a greater priority. So of course, because it is the greatest priority of all of our jobs, then we're going to place that as priority 1, and therefore it is the first thing that needs to go. Then we're going to process the next 2. So because the remaining are equal priority, we're now going to then do our second rule, first in, first out, as we saw with the regular queue. Now, because we've already established the position of the magazine, we don't need to worry about that. We just need to worry about our P2s. So which of the 2 came first? Well, the news one did. So that is going to have a higher order than the blog. So then now that we've figured out the actual news, we have the last remaining one, which is going to be the third order. So here, now that we walk through the steps, we have our order. It is 2, 1, 3. So when it's time to actually move things into the job server, well, our magazine is going to be first, then our news second, and then our blog third. So that becomes the priority queue. So again, that's the difference between a queue and a priority queue. With a regular queue, you follow first in, first out. With a priority queue, you weight it first, figure out the highest weight first, and then of the things in the same weight, you just follow first in, first out. And that's pretty much all we need to know about queues for now at a high level. We'll talk more about technologies that represent queues in a later video when we do a deeper dive into queues. But as far as we're concerned now, this is all they represent at the high level in our diagram. So we've learned about job queues. Now, I mentioned earlier that something has to be able to actually send the jobs into the job queue. because what is giving our queue the actual jobs it needs to do? This is where we come back to web servers. So I know I mentioned earlier that web servers are really driven by user behavior. You can kind of see sometimes that web servers might not always be driven by user behavior. They might also house some application logic, not just business logic, in the sense that a web server can be the thing that actually queues and figures out when to actually start setting up these jobs at some point. So if you've ever worked with anything like a cron job is a good example. Cron jobs are just jobs that run based on your commands for it at some point. So maybe, for example, we do and run this command every day at 12:01 a.m. We queue up our jobs then because that's when we know we'll have the newest, latest job posts for the new day. That might be an example of a cron job. That cron job could be set up on your web server. So your web server's whole purpose is to send these jobs into the job queue. However that happens, that is up to your actual web server code itself. But this whole thing is how the web server is connected to the job queue. And that's pretty much the relationship. So it could be web servers, it could be application servers. Again, we're splitting hairs here, but the main idea is just that you need something to send these jobs into the job queue. And that's that connection right now that we have between our web servers and then this leg of the job piece of our system. We'll dive into more of this when we look into deeper examples, but hopefully you at least understand how jobs work and how we have separate servers that pretty much handle the behavior of figuring that out. So there we go. We've understood jobs, we've understood queues, we've understood job servers. Now let's move on to the rest of this diagram. I'll see you in the next video. Welcome back, everyone. So far, we've actually covered quite a bit of the diagram, almost more than half. This is where things get a little interesting because we've covered pretty much the main components that you can use in order to build the functionality of a system. But now we're going to start splitting hairs a little bit and talking about some of the abstractions. And the best way to do that is to discuss services. Talking about services is interesting because a lot of what we build are services. You've heard about services in microservice architecture, which we'll discuss a little later. But for now, let's understand how services fits into our overall diagram and architecture. So web servers communicate with services. And generally speaking, services, because I've chosen this diagram, which looks like a nest, the reason why I want to show you this diagram is because it kind of looks like the actual overall diagram we have been looking at so far. Services encapsulate pretty much all of the components that we design in systems, but as a service. So let's talk more about what it is that a service is in the first place. So in order for us to understand this, let's go back to our Facebook example. When you think about these features that exist inside of Facebook, we can focus on some of them. The one I want you to think about right now is actually the profile or the user. When you log in as a user, what you are doing is you are authenticating yourself. Email sign-in, single sign-on, authentication through a third party like Google, or I guess in Facebook's case, you would not authenticate with Facebook, but you've all seen Facebook authentication before. Generally speaking, these are all authentication methods, and authentication itself is a service or entire feature in itself. So here we can see authentication. I'm just going to keep it separate for now. We'll discuss this more a little later. We already have become familiar with the newsfeed. So when we think about what we get as a personalized newsfeed, we've been discussing this feature quite extensively and using it as the main example when we explore our diagrams. So I want to keep newsfeed as another feature or another service. Finally, when you think about Facebook, a very popular feature that we commonly use in Facebook is the messaging application. Now, the messenger or the messaging feature is a feature that lives inside of Facebook or even inside of your iPhone. If you look at the apps, the messenger is even an entirely separate app. But as far as Facebook as a feature goes, it is a feature that lives within Facebook. So here we can say that we have Messenger as another feature. Finally, The last thing is on the side of Facebook, there tends to be a bunch of different communities you can join, maybe even the marketplace. There's all these different large built-in features that involve you interacting with other users. This I'm just going to group under communities as a feature. But here we have 4 of the main features that make Facebook what it is as Facebook. Generally speaking, we're familiar with using them all inside of one system. But what can happen is you can actually isolate each of these into their own independent system or service. And what we're going to discuss is primarily authentication and newsfeed as 2 different services to better understand what services are in the first place. Services are a little complicated speaking about them at a high-level abstract point of view, so I'm just going to give you a direct example and we can dive deep into what services are and how they fit into our overall system design. So now that we've at least taken a look at some of these examples, in the next video we're going to talk about how we can actually design each of these individual services so that we get a better understanding of services altogether. So I'll see you in the next video. Welcome back, everyone. So continuing our discussion and understanding of services, we are going to design how these 2 authentication and newsfeed features can be built as their own service, using all of the things that we've learned so far about the different components in a system. So to begin with, I want to talk about the newsfeed. So when you think about a newsfeed, this is pretty much the main thing we've been exploring and using as the main example to learn about the components of our system design. So we know that entering into our newsfeed service, we receive requests from wherever, most likely from a browser or client, to get posts. So this comes into our system and it hits our load balancer first. Our load balancer will then communicate and split up this load of requests to numerous amounts of web servers. These web servers, of course, are horizontally scaled, which means there are multiple of them. These web servers then all interact with the database, and the database houses all of the appropriate data for the posts. Our web server also will interact with a caching service so that we can optimize and figure out which groups of posts can be cached and are either regionally split or group-wise split amongst multiple users so that we can improve the user experience of serving them cached data instead of, again, the extensive service of interacting with our database. Then we also make sure that our web servers communicate with the job queue, and the job queue fires off jobs to the job servers, and these servers will then finally interface with the data sources where we get the appropriate posts so that we make sure that our database is up to date. The job server will extract the appropriate posts and then store them in the database so that our web servers can make sure that they're always extracting the latest posts that it needs in order to best satisfy this newsfeed service. So this, in a nutshell, is pretty much what our newsfeed service is doing. That's a design using all the components that we've seen so far. Next, what we want to explore is we want to talk about the authentication service. So this authentication service, similarly, we're going to receive requests for logging in. And for now, let's just focus on a very basic login, that's email and password. It's going to come into our system, our authentication system, and it's going to interact with the load balancer. The load balancer is going to work with web servers, again, numerous web servers that run application logic or business logic that have to do with logging the user in with email and password. Now, in order for us to verify this, we need a database to keep track of all of our users and their appropriate emails and password. This is pretty much all we need. It's a very simple system for logging and authenticating users. Now, this right now is just one-factor authentication using just email and password. It's very rudimentary, and there's much more significantly complex versions of authentication that we can do or authorization, but we'll discuss those much later. For now, as far as our understanding of authentication goes, we all know email password login, so we're just going to keep it simple for this authentication service. So now that we have this combined with our newsfeed service, we can now think about how our overall system is comprised of these 2 services. And then, of course, our application system, meaning our overall system of this Facebook application that we're looking at, is pretty much containing these 2 individual services inside. Now, again, what we've done here is we have built 2 separate services that serve 2 separate features. This is where we can start to understand services a little better. A service is essentially, you can see it almost as a complete project. It's isolated in the sense that it focuses on one singular responsibility. When you think about the term microservice architecture, what you're doing is you're building your system as a composition of small services. And a service is a self-contained deliverable system. And the whole idea of that service is that it does one thing really well, or one domain. So authentication can be a domain. It specializes in figuring out users and what they have access to. So when you try to log in, well, you're always going to interact with the authentication service because that logging in feature is something that the authentication service specializes in. The newsfeed service doesn't need to do any of the heavy lifting when it comes to figuring out how to log in a user. Why would it need to govern that? The newsfeed service focuses purely on everything related to the newsfeed. But as we're going to see, maybe the newsfeed service benefits from some of the things that the authentication service can provide it. Where this lies is in the fact that when we think about our newsfeed, again, it's a personal feed, meaning that there are very specific posts to the user that we want to return. Now, how that works is going to be through an access token system, which we're going to walk through to understand how inside of our system, these two separate services interact with each other. So here in our application system, we're going to add in load balancer as the entry point. And we're also going to add web servers. So here, let's walk through the logic of what these two pieces do when actually interacting with the overall system. The web servers, of course, communicate with the two services, the authentication service and the newsfeed service. And when we look at how a browser client makes requests now with our overall application in a more realistic example, we'll see how this all works. So the browser client, when you land on Facebook for the first time, what you want to do is we always prompt them, can you log in first? Because everything begins only when you've logged in and we know who you are. So now the login request comes in through the load balancer, which gets sent to the web servers. At this point, the web server now has to decide, this is a login request. What am I going to do with this? Which service gets the login request? Obviously, the authentication service. Again, we've split up the responsibilities. The newsfeed service does not need to do anything with logins. So this login request gets sent to our authentication service. And then our authentication service will send back an access token. Now, this access token gets stored on the browser client. So what is an access token? Well, an access token is something that allows our system to know that the user is who they say they are. It's something unique generated by the authentication service, and the authentication service holds onto for a session of the user so that we know that this user is who they say they are without them having to constantly log in over and over again. And now when this browser client requests posts from our system, it gets an access token attached to it. This access token goes with the requests in order for us to verify that the user can get what it gets. So here, this then gets passed to the web servers again. The request comes through the load balancers. And now what happens when the web server receives, hey, I'm getting a request posts with the access token. What we're going to do is we're going to first have to verify that this access token is a valid access token. So the web server will send the access token to the authentication service. The authentication service will then verify whether or not this access token is valid. If it is, it sends it back. Sometimes this access token is modified with permissions in order for us to make sure that we know what permissions are allowed on this access token. The reason for this is so that we can verify in our other services what the user has access to. For example, with the user A, they shouldn't be able to access posts for user B, C, D, or E. The access token is what's going to dictate what this user has access to. The newsfeed should not have to entirely be responsible for that. Sometimes it is. Again, it's context-driven. We're just walking through an example here. Now that we have our up-to-date and verified access token on our requests, then finally our web server knows, okay, I'm going to pass this request into the newsfeed service. The newsfeed service then again sees that the access token is verified, so it now does what it needs to do, goes through its logic, and then extracts out the required posts that our browser asked for, and then sends that back. And our web server finally sends that through to the browser client, and now our browser can actually show the appropriate posts. And that is the new flow of how you break up all of this system that we've looked at into services. And the reason why we walk through this example is because this is a very common division of labor in a system design. Authentication service is almost always its own service. But hopefully now what we've looked at is how services operate. What is that abstraction of a service? Again, it's where you break up your features of your website, or you break up the different components, like large level, high level components in your system, into more independent services. And a service, again, is a self-contained system that delivers a very specific functionality, and you do it in a way that other services or other systems can utilize it and communicate with it for that intended purpose. The easiest one to look at is a newsfeed service or an authentication service. Authentication as a service is a system that solely cares about authenticating the user and figuring out things related to the user. And now with the authentication service being good at its domain, other services and features can rely on it to help them be better at their function. As we saw with the newsfeed service, it can now rely on the authentication service to identify the user being who they say they are, but also it can determine through the authentication service the level of access to provide to this user when it comes to what posts to give back. And this style of microservice architecture is extremely common at scale, which is why it's such a key component of system design. By breaking up your system into smaller services, especially at scale, you can picture how a lot of these websites build very large, complex, robust features. By having this separation of responsibility into individual services, you're able to have teams hyper-focus on improving those individual domains as services. With this being such a crucial part of system design, throughout the rest of this course, we're going to hyper-focus a lot on breaking up features into services and thinking about services as a cornerstone of how to design our system. But for now, this I felt like was a great time to just get into our minds the idea of abstracting services. We've learned a lot about how these components build into systems, and services is kind of like a higher level abstraction from these smaller components that we've looked at so far. Again, these different services are often microsystems in themselves. Just as we saw, we designed 2 different services with the components that we've already worked with, and we fit them together into a larger system that we are very familiar with, even just as users. So now that we understand services at a high level, let's continue with the next topic in our system design. I'll see you in the next video. Welcome back, everyone. So as we are approaching the end of this diagram, we are going to start touching upon the final topics here. And these ones are a little easier to understand. Everything we've looked at so far is actually the major components that live inside the majority of systems. The remaining ones now are additional, I would say, must-haves at systems of scale and many large products, but they aren't 100% necessary, but they're quite easy to understand. So what we're talking about next is data hose and a data warehouse. So when you look at this system here, what you see is the browser client to the load balancer to the web server, and then the web server communicating to the data hose and the data warehouse. For simplicity's sake, let's remove the load balancer. I'm removing it just so that we can see how the browser client and the web server directly interact with the data hose and the data warehouse. But let's talk about what that data hose and data warehouse are. First of all, let's talk about data. What is the data? As you know, many companies and the tech industry today live and die by the data they collect from their user behavior. Whenever you interact with any part of the application, when you click buttons, when you interact with news feeds, when you interact with a search bar and the things that you search, and then the different links that you click and when you click them, any interaction that you have on the website, companies are trying to extract that data, collect that data, store that data, synthesize that data, and then analyze that data to better understand user behavior. Many companies even sell that data to advertisers in order to get more profit, because at the end of the day, When they're able to understand the user's behavior, they're able to make a profit or improve the product. But how do they gather this data? Well, as I mentioned, there are numerous ways that you can do it. There's numerous solutions out there. All of us have heard of Google Analytics, which is one very common solution, but many companies roll their own. In order to roll your own, you are going to utilize a data hose and a data warehouse. So here underneath web servers, you'll see that I put behaviors. Essentially what's happening is that they're trying to capture in this moment whenever the web server does some type of interaction. Like imagine you were making a payment. When that payment is going through, or whenever a query is going through for a user, the web server, as we know, holds a lot of that business logic. When that business logic is firing, there may be a chance to generate that raw data. That raw data will just have details regarding what that event is as far as the need to store it goes. It then gets passed to the data hose, and then the data hose will pass it on to the data warehouse. Now, we can do this through the web server, or we can do this directly from the browser client. I'm showing you this line cutting through because depending on where you host your data hose, you may be able to expose it publicly. Chances are it's also going to go through web servers, or it might go through some other entry point inside your system. But the key thing here is that you can also capture user behavior directly in the application. It doesn't always have to be fired through the web server. You can also easily fire it from the front end. That's why I'm drawing you this line. It's more metaphorical in the sense that you can easily imagine how with Google Analytics, you run the library directly on the front end application and then you fire off data into the data fire hose. Same thing happens here. It's just instead of using Google Analytics, if you're rolling your own solution, you would of course fire off this raw data that encapsulates the user's interactions into the data hose. Now, regardless, whatever means you get that data into the data hose will then take the raw data and massage it into a format that is more readable, or it's in a format that we want to store in the data warehouse. But we still keep the raw data. And the reason why is because we're going to fire both of these into the data warehouse. And the data warehouse is just a storage solution. It could be similar to most databases. It's just depending on how you want to store your data, you might roll a different style of storage. But the key thing here is mainly just you have a data hose that is the entry point for all of the raw data of user actions or behaviors or just different events that are firing in your system. And then the data hose will modify and change the structure or massage the data in a way. And then you store both in the data warehouse. You want both the massage data, but also the raw data. And that's it. The main thing here, again, of why you do this is to collect data on your users and then synthesize it so that you can make better decisions off of that data. Now, what you do with all of this enormous amount of data is up to you and up to your system and up to your business goals. But the main thing, at the very least, as far as the solution goes inside of our system, is just that that's how we get it into the actual system design. So that's it. That's all the data hose and data warehouse do for us. So let's move on to the next topic. Welcome back, everyone. Continuing with our diagram, the next thing we're going to talk about is cloud storage. Now, cloud storage is actually pretty simple. Essentially what it is it's a backup source of data. And it lives in the cloud so that it doesn't live on a local machine that you own, or an on-site, as they're called. Essentially, everything we've learned about so far is when you build your own system. You can do this also on the cloud using AWS, Azure, Google Cloud Provider. Much of this diagram is pretty much going to be the exact same because it doesn't really matter where your system is hosted. It's either self-hosted or hosted on a cloud architecture platform. The main thing here is just that you want to have an additional backup, which is cloud storage. So other than the physical devices or the physical databases that you have, you might want to use an additional storage location. Another way you can imagine this is if there was actually a line also between the web servers and the cloud storage so that you can store not just the data coming out of your data hose, but also any data going into your database or from your services or from your job queues. Essentially anywhere that you can store data on your system, you can back it up on cloud storage. That's really all cloud storage represents. So talking about cloud storage, again, we can replace database, data warehouse. There's numerous types of databases, which we'll talk about later. And then data warehouse, as we mentioned, is just a place that we store all of our user data. But inside, you can store app files. You can store media files. So app files being the ones that we actually pass to the browser so they can build the website, whatever the final JS, HTML, CSS that we want to pass along are. We can store that on cloud storage as well. You might be familiar with Amazon AWS's S3 bucket. You can easily store those files on there. You can also store media files being images, audio and visual, videos. All of those different files can also live on cloud storage in a blob database. We'll talk about that later as well. It's just a type of database that can store these more complicated forms of files. We also have the raw data, as I mentioned, that goes into the data warehouse, or formatted data goes into also the data warehouse or the database. At the end of the day, the main idea here is that you can back up any kind of file or data into your cloud storage. And that is all cloud storage is. So now that we understand cloud storage, this kind of links to our last topic, which is the CDN. Now, the CDN stands for Content Delivery Network. And the purpose of a content delivery network is so that it makes it much more performant for us to deliver our content of our website to many different users all around the world. And the reason why, as you saw in the image, it was linked to all these other parts of the actual diagram is because you can store the files that you receive for the website into the CDN, either from cloud storage or from the load balancer. The main idea is just that the CDN is going to hold the files that you want to serve to the browser and not have the browser go directly to the web server. Instead, you just have it receive it from the CDN. Let's take a quick look at an example here. Let's say that we're looking at this world map here. And let's say that our origin server, which is where we host and we own the server that contains the most up-to-date files for our website. Let's say this lives somewhere in Europe. Let's say England, for example, the UK. Now, let's say we have a user that wants to access our website and they're somewhere in North America. Let's say they're somewhere in Canada. What's going to happen is that without a CDN, they're going to have to make the request directly to our origin server. Now, as we saw with our example before when we learned about web servers and serving this information directly to our browser, we make a request to the DNS. DNS then gives us the location of where the server is, and then the browser will make that request halfway around the world to get to the origin server inside of the UK. Now, this takes a lot of time because the latency of the travel time for a request to go through halfway around the world is very long. So what we can do is we use what's known as an edge server. Now, an edge server is a bunch of servers that live in different parts of the world. They are localized servers that hold the same type of information that the browser is asking for from the origin server. So now when this same user wants to make a request, what will happen is that the DNS will work with the CDN to figure out the nearest edge based on the user's location. Then it will then give the appropriate IP address so that instead of going to the origin server, it's going to find the nearest one that is also in North America, and then it's just going to make the request there. So this, again, is going to work for users all around the world, wherever they are. Now, without access to the CDN, if they were to make requests for the website, they would all have to pull against our origin server, which is really far. Depending on where you are in the world, you might be making an entire travel the distance of the world itself. Instead, because we have access to edge servers, they will instead just receive the IP address of their nearest local edge server. And this greatly increases the performance of our website because it drastically reduces the latency of all of these different users we have around the world. Now, you really leverage a CDN when you are much more global. You could argue that the majority of apps are accessible in theory to all users around the world because anyone anywhere can access your website. So should you always use a CDN? Because you do pay for the CDN. I do want to make that clear. And we'll learn about some of the complexities of running a CDN, mainly because in order to make sure these edge servers have the most up-to-date code, you have to figure out when to make these changes from your origin server and then deploying them to the edge servers. This is where some of the complexity of using a CDN is, and also the cost of using one. But generally speaking, whenever most companies roll out applications, they roll them out regionally. meaning that the actual marketing campaigns that they target are all centered around some specific region to begin with, most likely where the actual company is located to begin with. So CDNs typically come into play when you have large distributed systems where you have a lot of global usage. But this is all CDN is. And with this now, we have evaluated pretty much all of our web architecture components. So now that you understand all of these pieces, what we can do now is take a deeper dive into the core principles of system design. Because we understand what these components represent and how they work, it's much easier for us now to talk and discuss as well as understand how we want to actually approach designing a system in the first place. Because now we know the components, we can now understand why and how we want to use them in order to build systems effectively and efficiently. So join me in the next series of videos where we will do deeper dives into all these sections, as well as understand how we want to ground our approach to system design. I'll see you in the next video. Welcome back, everyone. So now that we've covered all of the high-level components that live inside of our web architecture of a system designed system, I want to talk about the goal of system design. Better yet, I also want to take this moment to reiterate what I mentioned in the very beginning of this course and what this course is for, because now is where we're getting into the meat of the actual course. System design is an incredibly expansive topic. There are numerous topics within system design that are very deep in and of themselves. The reason why I'm bringing this up is because many people trying to learn system design know that it is an interview that they need to pass to get into many of the FAANG or big tech companies. One thing I want to tell you about that interview as well about system design. System design and the interview is the true gauge of your seniority. That's why the system design interview only comes in from senior onwards, because the system design interview tests whether or not you've actually worked and contributed to distributed systems. When you are a junior to intermediate and maybe even to the early stages of a senior developer or a software engineer, you are mainly learning and working on low-level code. This is the code that you write, whether it be your application logic or your business logic that you write with the code for 90% of your working day. You might interact a little bit with some stuff from DevOps, some stuff from the CI pipelines, some of the things working with containers, maybe Docker, maybe some different Terraform file setups, or just different parts that kind of overlap with system design. There you get a little bit of exposure. But the true test for most seniors that they're looking for are for ones that have actually worked on large distributed systems. And that experience you cannot shortchange. You can accelerate the process, but you cannot get it secondhand. You have to get that experience firsthand. And I want to really stress this because no course is going to fully prepare you for how hard the actual system design interview will be if you do not have any experience building and working on distributed systems. The reason for that is because it's a very conversational interview. It is designed for them to figure out whether or not you actually have the chops, you actually have the experience to work on distributed systems. So that is a very, very important thing I want you to know about system design. It will only benefit you to understand that part of the actual interview. Now, this course is designed to be a more general approach to system design because it's meant to help you get more experience, or at least help direct the approach you have towards system design. This course is aimed to give you some of the core principles and at least some of the framework and the thinking around looking and evaluating design systems and distributed systems so you understand why they make the decisions that they made. It's just aimed at helping you better even perhaps consume existing blog articles or watching talks about people that discuss problems that they've encountered building distributed systems. So when they design the system of their applications, they're going to talk about the problem that they're trying to solve and why and how they solved it. So through this course, I'm hoping that because it will help give a foundation, a solid foundation, when you do end up consuming that media or even working on distributed systems yourself, you'll be able to learn more from it because you can glean and synthesize what you're experiencing in a way that's more valuable to you as far as learning system design goes. So that is the main point of this period onwards of this course that we're going to cover. We are going to tackle what it means to really understand what system design is for. So thank you for listening to my little tangent here, and let's dive into the goal of system design. So let's talk about the goal of system design. So here I'm going to put a little bit of text on the page because unfortunately we're going to have to go through the definition of why we need system design, but I promise you this is one of the only slides that is this much text. The goal that we have when it comes to system design is we want to engineer and build systems that meet the needs of the business in a coherent, efficient, and organized way. We do this by designing the architecture, the interfaces, and the data of the system. These three terms are very key: the architecture, the interfaces, and the data. And we're going to discuss what each of them represent. Before we do that, though, we need to ground our understanding in the core principles that drive system design. So there are mainly two that we want to focus on. There is availability and there is reliability. What you are trying to build the system to achieve is availability and reliability. You want to build a highly available and a highly reliable system. Of course, you want the system to also deliver the core function that your application or your business is aiming to achieve. But the main idea of why you're making these decisions in designing your system is so that you can maximize the availability and the reliability of the system itself. Now let's talk about each of them. Let's start with availability. Availability is pretty much the percentage of time within some given period that your system or application can actually be used and will perform the desired function of what it's supposed to do. So think about it like this. You have a system, an application that we've built, and you know that users want to access and use it for some specific purpose. If they're able to access it, then it's available. If they're unable to access it because maybe your system is crashed, your network is failing, your hardware is burning, whatever it is, then it is considered not available. So when we're talking about availability, we're trying to evaluate the percentage of time within some specific period that your system is up and running and performing the desired function. So this can be calculated with a very simple equation, which is the uptime divided by the uptime plus the downtime. Here, again, reiterating what percentage of our system is functioning in a given time frame. Now, the time frame is going to be the uptime plus the downtime because that represents the total amount of time that our system is trying to be accessed or accessible. Essentially, as long as the system has been in existence, that is uptime plus downtime. Now, functioning is just uptime because, as I mentioned, if there is uptime, then that means that that is when your system is accessible and operating. By taking this equation, let's plug in some values and understand what we're talking about here. Let's say that the uptime is 300 hours, and let's say the downtime, for some reason, let's say we had to roll some updates, and these updates put our system down, and in total it took 15 hours. The total amount of time, the time frame that we were actually trying to utilize our system was 315 hours. That is the total amount of time that we're trying to understand. Within those 315 hours, only 300 hours were available. The other 15 hours, our system was down, hence the downtime. When you perform this calculation, you get a value of 0.952. And when you convert this to a percentage, it's 95.2%. That means our system was available for 95.2% of the time within that 315-hour time frame. That is availability, and that's the main calculation. Now, the reason why availability was one of the core principles that drives system design is because we are trying to figure out with our system that we're designing how to make it as accessible as possible to people that actually want to use it. The whole idea is that we're focused on actually delivering the product. When you think about whether or not the product is good, that is product design. That is where you are working on the actual application and trying to figure out if the application actually satisfies the needs of the user. That is a completely different thing from system design. System design is pretty much you trying to figure out how do we make it so that our solution is actually available in the first place? Meaning that if a user wants to use it and they're requesting for the website to do what it needs to do or what it says it's going to do, is it going to do it for the majority of the time that I need it to do it? This is system design. How do we maximize the uptime? Now, generally speaking, when it comes to evaluating how much uptime your system has, you use the nines of availability. And this is pretty much just 1 to 9 of these nines. And this is the percentage of uptime you want to aim for. 1 9 is 90%, 9 nines is 99.999 with the trailing remaining amount of nines so that you get 9 total nines. Here, with this aim, you essentially look again within a certain amount of time. So within a time frame of 1 month, let's say, for example, how much downtime are you allowed to have? If you have 1 9, then you have 72 hours. Now, if you are at the maximum 9 nines, the most downtime you're allowed to have within 1 month is just 2.6 milliseconds. That means your system is down only for 2.6 milliseconds. 9 nines is an extremely, extremely difficult to achieve amount of availability. Most companies are aiming for maybe 2, 3, or 4 nines. Generally speaking, unless there are lives at stake, let's say for something like a life support device, then you need to maximize the actual availability of that system. Because if the system goes down, then people might be dying. And that is an extreme case where it's worth the investment. Because remember, the higher in the nines you go with availability, the greater the cost it is. It's really expensive to maintain that high amount of availability. Much of where you're aiming for in your availability depends on where the business is at as well and the context of what your business aims to serve. If you think about businesses like cloud architecture platforms, whether it be Microsoft Azure, Google Cloud Provider, or Amazon AWS, most of the services that they offer are around 2 to 3 nines, maybe 4 nines. And that is the maximum. And they are mission critical products that essentially the entire tech industry relies on for their apps to work. So this is even for them really high, just getting to 3 and 4 nines. Generally speaking, we consider most applications to be very mature if they're at 1 or 2 nines already. So that's just something I want you to keep in mind when it comes to availability. But what you're looking at is really just a calculation of how to determine how much your system needs to be up in order for you to hit these numbers. If we expand this out to 1 year, we'll see that these numbers are generally quite more forgiving. Even then again, as you go anything above the 4 nines, it becomes extremely small. There are such low amounts of downtime. Again, most systems don't need to be that available. But here, hopefully, you can see the value of why we look at availability to determine the quality of the system that we have designed. And what we're going to use this availability to help us understand is we're going to use it to ground and understand why we design these different components that we've looked at the way we do. Why the decisions that you're making revolve around achieving better availability. And that's why availability is one of the core principles of system design. So now that we understand availability, join me in the next video where we will talk about reliability. I'll see you there. Welcome back, everyone. So in the last video, we talked about availability. In this video, we are going to discuss reliability. Now, reliability is different from availability in the sense that reliability talks about whether or not within your system it crashes or it breaks down and creates some kind of failure or some type of error state when it is being accessed. And just like before, the way that we calculate failure is with this mean time between failure calculation. So this is for reliability. Mean time between failure is the total time in the service divided by the number of failures you have. So mean, of course, is the average time. So let's plug in some values here. Let's say the total time in service is 300 hours, and then the number of failures is 5. Now, when you do this division of 300 hours by 5, the mean time between failures is 60 hours, meaning that on average, the mean, within a 300-hour time period, if there are 5 errors, that means every 60 hours there is some kind of critical failure. So that means that your system's reliability in terms of whether or not there will be any kind of critical failure is this value of every 60 hours. Generally speaking, with this reliability calculation and mean time between failures, you're just trying to determine that within the actual available time period of your system from our previous discussion, how much failures are there going to be within your system? And that's the main thing around reliability. You're mainly just trying to figure out whether or not the system is actually reliable to perform the function without error. You want to reduce the amount of errors, or you want to increase the mean time between the actual amount of failures you have. Now, having failures in a system is inevitable. You're going to have servers that crash, you're going to have code that breaks, you're going to have data that gets corrupted, networks that fail, devices that overheat. There are such a large plethora of problems that can arise. So there is going to be a risk on your reliability regardless. But again, the reason why we talk about reliability, honestly, reliability is not as important as availability, because much of the ways that we can get around some of these critical errors, you can solve by also trying to make your system more available. This will be things like increasing fault tolerance, adding more redundancy in your system, which we'll discuss. I know I've mentioned redundancy a couple times here, but these are all different techniques that you can do that will increase the actual reliability of your system. But these are the two core principles that are going to drive pretty much every type of conversation around system design that we're going to have. Especially when you start going out there and you start reading different articles around some of the types of systems that people have built. What they're talking about is trying to design systems that are available and reliable and resilient and fault tolerant. So now that we understand primarily the core principles that will drive our system design conversation, let's start diving deeper into these different components and talking more about the actual parts of designing a system. So I'll see you in the next video.
Welcome back, everyone. In this upcoming section, we are going to talk about networking. Networking is essentially how one computer or system communicates with another computer or system. Now, two models we're going to talk about is the OSI model and the TCP/IP model. But we're going to take a high-level overview of these models and really pick on the parts that are relevant for system design for us as web developers. The reason why this is so complicated is because networking is one of the most intensely deep topics that are out there inside of system design. It's actually an entire career path where you can work as a network engineer. And if you work at companies that are really successful in this communication and the speed of setting up the systems of these communications, such as Netflix, you actually make an enormous amount of money in the industry because it's kind of a niche topic if you go really deep with it. But for our purposes, because we're focused more specifically on the web development side of it, we're just going to do a high-level overview to understand what they are and then draw the relevant parts so that we can apply it into our understanding of designing systems. We're going to start with the OSI model. And OSI stands for Open System Interconnection. Now, this is really a logical and conceptual model that defines the network communication between a system in order to communicate with another system. It's a general model. So you can kind of see it as a bit of a universal model in that sense for just general computer networking. And it breaks up this communication into 7 abstract layers that are pretty much structured on top of each other. And because it is a general model for communication between two systems, I don't want you just completely mentally locked into this idea of how the internet works, but more just in general about any two systems overall in the world. As long as there are two computers that are communicating, you can use the OSI model to abstract out how that communication is happening. So let's go through these 7 models. you essentially have, starting from the top down, the application layer, the presentation layer, the session layer, transport layer, network layer, data link layer, and the physical layer. Now, it's important to note that each of these layers has their own protocols. When you think about protocols, they're really just a set of rules that defines how this data should be structured and then communicated. So these are going to be structured in terms of the syntax, which is how it's written, the semantics, which is like what key terms there are that are holding some kind of meaning, synchronization of how this communication is possible, such as like how much data gets transferred at a time, and then other things like error recovery. These are all rules that define the communication of data at a specific layer. To give you an example, the application layer, which is this top layer here, this layer holds things that are closest to the user. So as we mentioned, users start interacting with applications, hence why it's called the application layer. But the applications themselves don't live on this layer. Remember, it's the data that is being dictated, like the protocol, the rules that dictate how the applications might receive the data. So a less abstract example would be a user uses something like Google Chrome, which is a browser. The browser utilizes HTTP, which we all know, Hypertext Transfer Protocol. HTTP is the format that the browser understands. If it is actually going to render a website, it has to receive the data inside of this protocol format. Now, the next layer is the presentation layer. This layer is also typically known as the translation layer. So the data that we get from the application layer is extracted, and then it gets manipulated and formatted so that it is ready to be translated across the network. Now, the thing here is that what does that transformation look like? This might be encryption or decryption or compression as we know it, or translation. These are all things that we do when we need to actually get the files that we're getting in the HTTP format into the browser. If you think about it, sometimes we gzip them. That's a very common thing that we do in order to compress data down. That all happens in the presentation layer. Now, this session layer is the layer that's responsible for opening and closing the communication between two devices. As we know with sessions open and close, and there's a certain period of time in which that connection is alive. So the session layer is responsible for making sure that it stays long enough, a session, in order for all of the data to be properly transferred and then closed off so it's not wasting resources when that part is done. Now, the transport layer, which is the next layer, is the one responsible for end-to-end communication between two devices. So the session is responsible for opening that communication. The transport layer is actually the one that's responsible for making sure that the actual communication happens. So this includes taking data from that session layer that we were talking about and then splitting it into chunks and segments before sending it to the next layer underneath. This is also known as the network layer. Now, the network layer is essentially the one responsible for communication between inter and intra networks. So what is an inter and intra network? Well, when you think about a computer system, inside there are numerous communications that are happening between physical devices all on the same network. So what I mean by an intranetwork is that if you think about LAN, that is a intranetwork. So back in the 90s and 2000s when the internet was slower, if people wanted to play video games with each other at the same time, they would use LAN, which is a local area network, meaning that they're all on the same network and the devices communicate to each other on the same network. So again, the network layer facilitates communication between major groups of networks. So if there was, for example, two separate LANs and they had to communicate with each other, the network layer is handling that. The data link layer goes a layer deeper, and this one is actually facilitating communication between two devices on the same network. So if the network layer above was communication between two separate networks, data link layer is now the communication of devices on the same network. And then finally, the physical layer has to do with actually transferring bits of the data into a physical cable, hence how there is a physical cable here. So this is where data gets converted into a bit stream, which is essentially a string of ones and zeros. And this physical layer is important because devices on it must agree to the convention of what the ones and zeros are distinguishable from each other in a physical device. So again, there are different protocols here. Now, if this is confusing at all, do not worry. Honestly, the OSM model is one of the most standard things that get used inside of the industry of computers and software altogether, but it's not always the most relevant to us as web developers, but it's still very important because it really helps us with things like security and also things like understanding where different errors and fragility in the actual overall system of delivering a web application can happen. It's not the most important for you to know all of it by heart for system design, but it's important that you at least understand conceptually what's happening when people talk about these layers, because you're going to work with people who are network engineers. You're going to work with people that are vendors trying to sell you devices that help make it easier for you to do things at different layers. Because all these 7 layers exist when you're building some kind of web application business at scale. Now, you might offload the majority of this work and take things for granted because you kind of just plug things in, such as your computers, your servers, your routers. All this stuff is happening for you. But in order for you to understand where there is attacks that can happen into your system at a large enough scale, you'll need to understand how this model works. Now, there is extensive information about this because this has been around since the 1970s, 1980s. So there's a lot of data about this. I don't think you need to know all of this in super deep detail. Honestly, the way I explained it is relevant enough for the purposes of this course. But if you want to go deeper, you definitely easily can. And if you Google OSI and you just start looking through all of the different things that have been written about it, you will slowly piece together a better idea of this if you have not already. Again, for web developers like us, it's not as relevant. The one that's more relevant is going to be the next model, which is the TCP IP model, and that's the one we're going to go into next. But again, I want to highlight this OSI model. It's just something that's helpful for you to frame your thinking around how these communications happen between systems. It's not something just happens simply, it's actually quite complicated. And I'm hoping that through this example of an abstract framework or a logical model that we see through the OSI, it just gives you a better idea of how you should approach understanding things like networking. So now that we have that, let's move on to TCP IP. Welcome back, everyone. We talked about the OSI. Now we're going to talk about the TCP IP, so Transmission Control Protocol / Internet Protocol. Now, the fact that it says Internet Protocol, we already know that this is relevant for us because everything we do is through the internet. We've actually already talked about IP before when we talked about IP addresses, the Internet Protocol. We've talked about the V4 and the V6 if you remember. For us, we need to understand this TCP portion. What is this Transmission Control Protocol? So Transmission Control Protocol, it's connection oriented, meaning that we're trying to essentially establish a connection between 2 different sources, and we want that data to be transmitted in both directions. So location A, or I guess device A, needs to be able to communicate with device B and device B to device A. We want to establish a connection between these 2 things, these 2 systems, computers, so that we can send data to each other over the internet. Now, the thing about TCP is that it has this built-in error checking and within the protocol itself. It's just designed to ensure that data does actually get transferred completely. It is the best protocol for the internet because on the internet, we want to make sure everything goes across. So we send data files, we send web pages, we send images, and we send it through the internet. We most likely almost always use TCP for that because the complete amount of data we want to send, we want to ensure that it is being sent. So let's walk through some of the rules of how this protocol of TCP works. So TCP operates when you think about it abstractly. Let's say you're trying to send message of some kind over to this other system from A to B. I'm going to use a metaphor actually here, where you can think about it as almost like delivering mail of some kind. And let's say this picture of this green envelope is the mail you're trying to send. Now, let's say what you do is you write down a message on this letter. What happens is that maybe this letter gets split up into chunks. It gets split into 4 chunks, for example, because let's say the letter is massive and for some reason we have to send it in pieces. Maybe we're sending a string of letters and you can't get the whole message unless you read them in order. What happens is that we need to send these from one source to the other. So here, imagine there are numerous paths. There are numerous ways we can get this message from one side to the other, or each of these individual parts from one side to the other. Each of these circles represents locations, and A and B represent locations on this map, for example. Now, IP, the Internet Protocol, as we mentioned, has to do with addresses. It has to do with knowing the location, the destination of where we're trying to send. So if we're trying to send our message from A to B, the IP address tells us actually the address of where we're trying to go. So we know where B is through IP. TCP has to do with ensuring that everything actually is getting sent to the final destination. So these pieces move through and maybe they take different paths in order to get there. Here, you can kind of see that these chunks are just taking whatever path to the final destination. But because we have the IP, we know what the final destination is going to be. But let's say one of our pieces gets lost and it goes to the wrong destination. TCP ensures that B gets all the pieces. If it doesn't, it has certain checks and balances inside of the protocol that will tell A, hey, I didn't get this piece. I need you to send it again. So you can kind of see this as some way for us to ensure that we're getting everything that we need. And then once it's together, TCP, this protocol, is also going to put it all together so that we can actually read the message. So that's kind of the purpose of what it's doing. This is a high-level overview of what the protocol dictates. Now, how this actually happens. TCP/IP, this framework, this mental model, is 4 layers now. So we talked about what it does, but here let's talk about the 4 layers, just like we talked about the OSI models in the layers. And remember, this is how computers connect to the internet and then transmit data between them. So we've simplified this, and we've kind of abstracted out these 4 layers in a very similar format. There's an application layer, a transport layer, an internet layer, and a network access layer. So here you can kind of see these layers mapping to the 7 layers. It's just that the application layer now represents the top 3 layers: the application layer, the presentation layer, and the session layer of the OSI model. Remember, application is the layer that dictates the protocol that the application needs. Presentation is what converts the actual data coming across into the format that the application requires, and vice versa. Session layer is what maintains the actual communication session open so that all data gets properly transferred. So this is now represented in all together the application layer of the TCP/IP model. The transport layer is still the same. The internet layer is the same. So again, application to internet, there is a translation that happens here. And there's also movement that happens here. Movement happens at the transport layer. The transformation happens at the internet layer. So this is where we convert what the application understands into the data format that the actual network understands. So that is happening at those 2 layers. And then the network access layer contains the data link layer and the physical layer, which, as we know, has to do with the actual physical device as well as communication between 2 devices on a network. So those are just being abstracted and contained together. Now, if this is still confusing, remember, this is logical abstractions. This is a logical model that explains how communication happens between 2 computers. It's just that with TCP/IP, we're specific to the internet, whereas with OSI, it's any kind of communication between 2 systems. Now, where this gets relevant for us is when we think about TCP/IP on the right-hand side, this logical model, again, captures some type of protocol. And that protocol that's relevant for us as web developers inside our actual system design, when we think about it, has to do with TCP and UDP. These are 2 actual protocols that exist in communication at that internet level. So this is what we're going to talk about in the next video. But before we move on, I do want to stress that you just need to understand how these layers are important, because as you read about system definitions and you read about different designs of systems, different networking communication problems that get solved, they're going to talk about at what layer some of these things exist. All you need to know is the definition of that layer, and automatically it will slowly start to make more sense. It's just something important for you to know and hold as some kind of principle in your mind of a framework that exists between communicating of two systems. So that's it. The actual more relevant practical information is going to exist in this TCP vs UDP lesson we're going to talk about next. So with that, I'll see you in the next lesson. Welcome back, everyone. So in the last video, we talked about TCP IP. And you remember when I showed you that example with the mail, where we broke it up into kind of like puzzle pieces, and then I explained what TCP does and what IP does? So TCP IP, you can see as TCP. UDP is a different protocol, UDP IP. You can pretty much see it like that. But the whole idea between these two is the way that we get data from one computer to another over the internet. And these two protocols are often used, most times even in conjunction in systems, but they're both used to get data from one source to another. And for us, because we talked about TCP a little bit more, where it's connection-oriented, meaning that we need to establish that connection between device A and device B, and also we need to transmit data in two directions. A can transmit data to B, B can transmit data to A. So let's go a little deeper into that so we understand how that works. So let's say we have our client and we have our server. Again, we're talking about two computers, right? And I mentioned that clients, which is the actual user's computer, and servers, which is where we are probably hosting all of our web applications, both of these are computers. So here, when we want to communicate from one to the other, what needs to happen is that the client most likely is going to try and establish a connection to the server. And the server, once the connection is established, understands, and now data can get sent both ways. Client sends requests, server sends responses. This data flows in two directions. Both are able to receive and send data to each other. So remember, the key thing about TCP, it's a two-way connection. Data can go both ways. Now here, in order for this to happen, we need to make sure that we're actually on the same page. And remember, the main thing here is that we need to ensure that we are getting the correct order of data. We need to ensure that the data is all received. So this happens through the establishment of something called an ISN, which is an initial sequence number. Both the clients and the server both have their own ISN, and it's a randomly generated number. It's just a way for us to track on the server and the client whether or not we have received the correct ISN from the opposing system. So if the client wants to send data to the server, it's going to send its ISN. So the server is then going to respond to me like, hey, I did get your number. I'm ready for whatever data is associated with this number. Because as the numbers change, it knows what the corresponding data for that number will be. So remember, we're just using the number, the ISN, to track what the data is going to be. And because both sides are trying to send data to each other, they both need to keep track of each other's ISN for that connection. The ISN represents the data being sent over for that current session connection that is established. A different connection is different data altogether. So that's why the ISN is also randomly generated, because they don't really correlate to each other as far as sessions go. Like the connections between each other, we don't really care. Once one session is done and the next one starts, there's no correlation between those two sessions anymore. The actual TCP just governs essentially what's important within one connection session. The client wants to establish the connection to the server. So it will randomly generate an ISN. Let's say it's some number X. Could be 1, 2, 3, doesn't really matter. It's just some value variable X. It will then send a synchronization request to the server with that ISN as part of the package. So part of the data that's being sent is the ISN itself, the number of X. It'll be like, hey, my ISN number is X. I want to synchronize with you, SYN. I want to synchronize with you on the server. The server is then going to receive that value, see the ISN. It's going to say, oh, I got X. I'm going to acknowledge that I got X. Now, the way that I acknowledge that I've received this synchronization request with this number is I'm going to add 1 to this number. That's just how the protocol works. You don't want to think too deeply about why these things are specifically done this way. Again, they're rules. So the way that this rule set dictates that this happens is that once you increment this number by 1 and you acknowledge back to the client that this is what happened, then the client's like, okay, I've properly synchronized with the server. But now remember, this server also wants to send data back to the client. meaning that it itself also needs to synchronize back with the client with its own ISN number. So the server will generate its own ISN number as well. Y, for example, let's say it's 999. And then it will also send as part of that acknowledgement back to the client also a synchronized message as well saying, hey, my ISN number is Y. The client has now done two things. It's recognized that it's been acknowledged of this value X plus 1, but also it's going to acknowledge that the server has sent it some ISN of Y. So it's also going to now send back an acknowledgement for Y plus 1. Now realize in this acknowledgement message says, hey, I acknowledge that I'm ready for X plus 1. And our client is saying, hey, I acknowledge that I'm ready for Y plus 1. The reason for this is because now when we send data between the two servers, we're going to send it with data including the ISN of X plus 1. And similarly, the server is going to send data to the client with ISN of Y plus 1. The moment that we receive data and we see inside that this ISN has the actual acknowledged ISN numbers incremented, we know what session, what data is correlated to in our communication. So this protocol gets established this way. This really sounds a lot more confusing than it is, but it's really quite simple. Our client is saying, hey, for this current session that I'm sending you data, I want you to know that the data is associated to 1, 2, 3. So the server is going to be like, oh, 1, 2, 3. Okay, I'm going to accept that. I acknowledge that. And for the session, I'm just going to say, when you send me the data, send it to me with the message 1, 2, 4, so that I know to correlate that to 1, 2, 3, what you sent me. So within this range of some ISN number plus 1, our respective systems know what the correlated data when sent is associated to. The reason for this is because data gets sent in chunks. It doesn't always get sent in one giant message. Remember, this TCP is a connection. That means there's an open and a close. That's why I keep saying session, because the data keeps transferring between the two sides. It only closes when we recognize that it's done. So if we're sending numerous packets of data once this connection is established, that data, as we saw before, can get pieced back together. It might get sent in 4 different pieces. But again, some data might get lost along the way. So we don't close that connection until we have all of it. And as I mentioned, TCP is waiting. It's doing polling, essentially. It's saying, hey, I'm supposed to receive 4 pieces. I only got 3, and I'm missing the 4th one. Can you send it again? But because we're receiving numerous data, potentially, maybe over multiple connections, how do we ensure that we know that the data we're receiving, which one to associate it to? We associate it by this ISN number, and the connection, the session that is established has some associated ISN number. And we use that plus 1 as part of the data so we know what to correlate to what session for. Now, I'm really just showing you this because I think it's important for you to know the mechanics of why this guarantee of data delivery is happening. And the majority of web applications are really going to use TCP. Examples of TCP, this protocol, is HTTPS and HTTP, which we're all very familiar with as being what sends much of the website data between the server and a client. The reason why this is the case is because when you think about the user experience, you need to guarantee for the user that all of the data they need in order to enjoy your application is actually being sent over. If you think about sending a React website, for example, what if we break up the packets? As we know, we chunk data all the time, and we send it over the network. It doesn't even matter if we chunk it. Most likely, it's going to get chunked in some way. Let's say some of those chunks don't make it, and they contain the core functionality of the React package. The entire website is just not going to function without that complete amount of data being sent. So that's why TCP, with its guaranteed delivery of data, is so critical and pretty much what drives the majority of the web. Now, you might be wondering, well, if it's not TCP, what's that UDP one you mentioned, Yihua? So that's what we're going to talk about in the next video. There's limited use cases of when you use UDP, but it is important and it is used, especially in the future. And we're going to talk about why, because it is faster than TCP. And we're going to talk about all that in the next video. But for now, I just want you to understand with TCP what's happening here and just really focus on the fact of guaranteed delivery of data. One other thing about TCP as well, as with anything in networking, I've given you an overview, but this topic is incredibly, incredibly dense and deep. Do you need to go this deep yourself for system design? Most likely not, but it's still something that if you're interested in and need to, it is something that is a very deep topic. But for our needs, this is enough for us. So let's move on now to UDP. Welcome back, everyone. So now that we talked about TCP, I want to talk about UDP. UDP is also an internet protocol. It stands for User Datagram Protocol. Now, the thing about UDP is that it's much faster than TCP because there is no connection. This is a connectionless protocol. What this means is that, remember with TCP, we talked about how there is that 3 handshake of the synchronized acknowledgement synchronize that happens, which establishes a connection between the client and server. And then we're constantly maintaining that connection until all data related to that session is complete. We don't do any of that with UDP, meaning that there is less resources consumed in order to maintain that connection between the client and the server. I'm going to call it a session because it's easier to think about it as a session. There's no sessions in UDP. What happens with UDP is that the client sends a request to the server. That request essentially allows the server to know that there's a client out there that wants some data. What's going to happen is that that server is now just going to keep bombarding the client with data. It's just going to keep sending it over and over. Whether or not that data gets over there, the server does not care. It doesn't actually need to guarantee that data delivery. All it says is that I'm just going to keep firing data in that direction so that hopefully the client gets all of it. If it doesn't, though, that is not my problem. It is a much faster and simpler, and you can say it's a more efficient protocol because there is no connection here. That server will just keep sending and sending and sending data in that direction, hoping that the client gets it. But if it doesn't, that does not matter to the server. So here, you don't get guaranteed data delivery, and there's no retransmission at all. Because again, how do we know we need to retransmit if we don't even know that the client didn't get some part of the data? That is pretty much the thing about UDP. Now, the reason why you would use UDP is when you need some type of protocol where you don't care about the data being guaranteed. This is where you're talking about things like video streaming, live streaming, a voice over internet protocol like VoIP. These are all use cases for UDP. When you think about a live stream, the most important thing is that it's live. You don't care that if in the middle of that transmission, some of the data gets corrupted and doesn't get sent over. It's just going to get corrected later anyways, because if you ever watch live streaming, you've seen before sometimes the video glitches out a little bit, but then it just continues live. In that moment, you as a user, you do not care that maybe you missed that section as much as you care that you're seeing live what's happening. Now here, that's pretty much the main difference between TCP and UDP as far as the use case goes. Generally speaking, you're going to use both sometimes depending on the needs of what you're building, but the majority of the time, you're pretty much just going to use TCP unless you're trying to build some live streaming service, then you're going to use UDP. And even then, it might vary depending on the use case. Again, it's context driven, but that's pretty much TCP versus UDP. These are two of the main protocols used in the internet. So the main thing you want to remember, if you care about the guaranteed delivery of data, TCP. If you don't care about that at all, and you want the speed and you want the performance, but data consistency and the overall delivery of data does not matter, then UDP. And that's it. Now let's move on. Welcome back, everyone. So in the last few videos, we talked about networking and we understood more about some of the logical models and the communication protocols between systems and computers, specifically over the internet. In this video, we're going to start diving back into the actual components in our system and starting with load balancers. Now, in order to do a deeper dive into load balancers, we need to talk about proxies. So what is a proxy? A proxy is essentially a new component that helps us achieve some specific goal. And there's two types of proxies, which we'll cover. To begin with, in order to understand it, we need to reestablish a diagram, a very simple one though. On the left-hand side here, you see different types of clients. So whether they're tablets, phones, browsers, etc., I want you to see it as the users that could be trying to access our servers. So the users will try and access it always through the internet because we're talking about web applications here. And on the right-hand side here, we have the servers that represent the different application servers or job servers that we have. That part doesn't really matter. It's just whatever hosts our actual application. Now, a proxy, there are two types. There are forward proxies, and then there are reverse proxies. But we'll first start with a forward proxy. The proxy is something that sits between the clients and the internet on the left-hand side. So it's not in our system. It's on the client side. What this proxy will do is it will communicate between the clients and the proxy and the internet. So the clients now will never directly access the internet. They'll have to access it through the proxy. From here, after the proxy sends the request to the internet then forwards these requests to our servers in our system, and that part is completely irrelevant to the proxy. The main thing about the proxy is that the proxy will hide the details about the client, or at least it can, from the internet and the servers. The main thing you need to think about a proxy is that because it sits in front of the clients before it accesses the internet, it can modify all of these requests. It can change them, it can update them, it can hide details about them. And the main thing is that the internet and our servers that see these requests, they will see them all come from the proxy, not necessarily from the clients. Now, the proxy can forward the details of the client if it wants to, but the main thing is that the proxy has full control over the requests coming from the client now. So what the proxy can do is it can actually modify those requests. It can even essentially lock out access to a lot of different websites to the client because all of the requests are being seen by the proxy and the proxy has full control over them. That's a forward proxy. Companies use them in order to block websites from being accessible by users, maybe to protect some data. Schools use them so that students can't access things that aren't education related a lot of times. Proxies are used in many organizations for different purposes, but that's what a forward proxy is. For our intents and purposes, we care about a reverse proxy, where the proxy lives on our side, inside of our system. In this example, the clients access the internet, or maybe they access a forward proxy. It doesn't matter. The main thing here is that the reverse proxy lives on our side of the system. The internet will send those client requests to our proxy before it enters and hits our servers. The proxy will then forward the requests to the correct server in order for whatever behavior to happen. Now here, the main advantage for us is that because the proxy is the entry point into our system now from any of the requests from the clients, all the actual clients will see, or the internet will see when it gets responses back, is that anything comes from the proxy. So we can hide any details about where our servers are, location related. Maybe we can modify some of this data all on the proxy. And there are other advantages of a reverse proxy for us other than just hiding the details. So some of the things about the reverse proxy that we can do is if you are keen, might have realized that this proxy kind of behaves in a similar way to a load balancer because it's receiving all the requests as an entry point, and then it's forwarding these requests to the servers. So isn't this really similar to a load balancer? Well, this is actually very true. In a diagram where there's a load balancer that then forwards the requests and manages the load, but you can absolutely use a reverse proxy as a load balancer. In fact, many load balancers are reverse proxies. So let me give you an example. An example of a proxy software is Nginx. Many systems will use Nginx as a load balancer as well as a reverse proxy. So for many intents and purposes, that is one of the benefits of using a reverse proxy as a load balancer, is that you get the other benefits that come with it, such as caching. You can actually cache a lot of what you need to deliver to clients on the proxy. So before we talked about how there's a caching service that we can utilize inside of our system design, that caching layer can actually be the proxy as well. We can cache some information on the proxy so that when we receive requests, we just forward them from the proxy. And that is way faster than having to forward the requests from the proxy to the servers and then the servers doing their long-winded thing of gathering that required build in order to send those files across. So that's another advantage of using a proxy. You get the benefits of a load balancer, but you also get the benefits of said proxy. So now that we understand reverse proxies and load balancing, Generally speaking, in many systems that we design, we're probably going to use a reverse proxy as a load balancer. So when you think about a load balancer, you can also think about using a reverse proxy in that place. Even beyond the caching benefits as well as some of the security benefits of using a proxy, the other advantage a proxy has over a load balancer is that a load balancer requires there to be numerous servers for it to be useful, because a load balancer needs to manage the load across multiple servers. But you can get the benefits of a proxy even if there's just a singular server, because you still get access to the caching and you still get access to the obfuscation of our actual servers from the clients. So for all intents and purposes moving forward, the majority of the time when I talk about load balancer, now I'm just talking about using a reverse proxy in that place. So there we go. Let's talk now about some load balancing strategies, because we're diving back into load balancers. So join me in the next video where we'll talk about that.
Hey everybody, I want to take a quick break here. Go grab a coffee, grab a tea, just take a break from all the learning that you just did. And I want to talk to you quickly about imposter syndrome. It's this idea that you're not good enough, that things are too complicated for you to ever achieve what you want to achieve. You look at other people, at other industry experts, and you say, I will never get there. But it's just a symptom of learning. This idea of you not being good enough simply means that, well, you're just not there yet. Things take time. If you want to learn a valuable skill, well, it's hard work. That's why it's valuable. Remember how you felt on the first day of going to school, first day on a job. It's the same experience. But over time, with repetition, with practice, you get comfortable, you get experience, and you slowly start to lose that imposter syndrome. Now, this idea of an imposter syndrome is great. It means you're doing something worthwhile. So don't use it as a negative. Use it as an encouragement that you're doing something good, that you're learning and you're stretching your limits. So with this break, I want to propose that we do a quick exercise. I want you to stop the lectures. Again, grab a coffee, grab a tea, and head on over to our Discord. Now, in our Discord server, if you've used it up until now, that's great. If you haven't, head on over to this server, and I want you to do something that I think it's super important to learning. And that is using what you've learned up until now to actually teach someone or help someone. So you can go all the way to, let's say, the coding and courses section and pick a topic that you want to help somebody in. So let's say you go to the Python channel. And in here, you'll have other students that are asking Python related questions. Now you can scroll through here and see if you're able to help someone. Even though you may not have the experience or the knowledge yet, this idea of practicing and explaining what you've just learned to other people, even if you're not 100% certain, actually is beneficial to your learning. Because if you're never teaching, if you're never explaining and vocalizing and showing what you've learned, you'll always be a beginner. This idea of teaching what you learn is a very important concept. So moving forward, as you go through the lectures, anytime you feel like taking a break, hop on over to Discord and help somebody. Our motto here is that we're always kind. We don't judge anybody. We're all just beginners here. We're all learning. So don't be afraid to answer things, because you got to remember, nobody's perfect except for Yoda. Yoda is pretty perfect. All right, I'll see you in the next one. Bye-bye.
Welcome back, everyone. In this video, we're going to continue talking about load balancing strategies and diving into some other alternate ways that we can expand the reliability of the systems we're building, especially at this level, connecting between load balancers and servers. So diving into this here, I've got this new component for you, which is the reverse proxy / load balancer that we were discussing in the last video. So here, if we were to put this inside of our system, we have requests that come from clients and the internet to our reverse proxy / load balancer. And then from here, we distribute them to our servers. Now we have, of course, web server 1, 2, and 3. Let's go over some of the strategies we already know. We've talked about the round robin before, where requests essentially just get evenly passed over one by one to every server in the list. So this is a very rudimentary strategy where we try and balance the load by just making sure that every time we get a request, we send it to the next server in the list. Now, the problem with doing it this way is that the servers themselves are often independent of one another, and they do not have any knowledge of the other servers. As a result, it's very easy to have some type of issues within the structure of doing round robin, because these servers oftentimes have different amounts of resources, bandwidth, etc. Just because you assume, even if the requests are the exact same and consume the amount of resourcing, the servers themselves might have a different amount of resources available to them individually. This is one of the key problems inside of doing this round robin strategy, and it's also one of the factors we have to think about with a load balancer. So I mentioned earlier that these servers do not know about each other. They don't know how many resources are on each other. This is due to the fact that, generally speaking, load balancing is designed to be simple for the actual execution in the architecture. Because the servers don't know anything about each other, they don't know when other servers go down. All they know is that when I get requests, I handle them. I don't know how many other servers are being utilized right now in order to serve requests. All I know is that when I get requests, I deal with them. I'm only focused on myself. This is fine. We just have to adapt some of our strategies and some of the potential load balancing techniques that we use. Another load balancing technique is known as weighted round robin. So here you'll notice on the left of each server, I've assigned a weight. Now, this means that the servers themselves are assigned a certain amount of weight depending on how many resources they have. The higher the number, the more resources. So here I've said that server 1 gets 3, server 2 gets 2, and server 3 gets 1. What happens now is that when we send requests, we're going to send the amount of requests equal to the weight in each run. So let's see what that looks like. So first, server 3 is going to get 3 requests, then server 2, 1, then server 3, 1. And that will be 1 run. Essentially, what happens is that as requests are coming in, we're just going to send 3 to server 1 first, and then we're going to send 2 to server 2, and then 1 to server 3. So then if we keep going further, you'll notice that that's what happens every time. We're going to send 3 to server 1 before we send 2 to server 2, before we send 1 to server 3. And then we're going to send the next 3 to server 1, and then to 2 to 3 again. This works as long as you're able to actually create a proper value and weight to assign to each server. We do this weighted round robin because it's a very efficient way of not overloading all the servers evenly, because generally speaking, most servers are not equal. The other advantages here is that we can easily A/B test things, because let's say server 1 has the new changes that we want to make, and we want to route all, or not all, but we want to route a majority of traffic to server 1 so that we can test and see what's happening here. Maybe server 2 has another change we have, but we don't really want to route everything there, and then server 3 has the old website. Here we can route accordingly, and then we can A/B test based on the data of the performance. So this is another good thing about weighted round robin, and just this general style of breaking up the traffic unevenly based on server capacity or server need. Finally, the other one we saw before was least connections. This, of course, has to do with either sessions or, depending on how many requests are on the server, we determine that we pass requests to the one that has the least. So here, between server 1, 2, and 3, 3 right now has the least, so we're going to pass the request to server 3. And now what we notice is that when the next request comes in, it's really just server 2 that has the most connections. Between server 1 and 3, both are valid to go because they share the same number of connections. So here, we can just rely on round robin again, or even weighted round robin, we can do that too. We can mix the strategies together. For us, if we just went with round robin, we would just pass it to the next one in the chain, which is server 1. And that would be it. This is least connections. Now remember, you can combine some of these strategies together for load balancing, and then there's a few others that are not uncommonly used, but you can easily now start looking at different load balancing strategies that exist. There's honestly a lot of different algorithms for load balancing. It's one of the topics that is the most widely attempted in many different circumstances with many different algorithms, but the ones that we've covered here are the most common ones. One additional strategy has less to do with how we balance load, but also related to load balancers altogether, but more so from a system design standpoint. Here, we've looked at these load balancers as they are. But one thing I want you to notice is that there is a single load balancer here inside of our diagram. If this load balancer crashes, which it can, any component inside of the system can overload, go down, or suffer a critical failure, whatever. In this case, the entire system breaks. What we call this is a single point of failure, when you have a single component that essentially can go down and then destroy the functionality of your entire service, or at least a core functionality of your service. In this case, what we want to do is we want a redundant backup load balancer. So all this means is that this load balancer is not used. When requests are coming in, we rely on the first primary load balancer. If this load balancer gets overwhelmed and it crashes, what we can do is then swap it out for the backup load balancer, and now essentially the behavior will continue while we try and resolve the issue going on with the broken load balancer. So this redundancy allows us to reduce the single points of failure. Now again, maintaining a backup load balancer increases the cost because it's an increase in complexity, and it also adds resources that we need to spend to maintain a passive backup load balancer. But unless you're designing for a system that has very low traffic or a very limited chance that your load balancer goes down, you almost always want to have a backup load balancer just to reduce this single point of failure or eliminate it altogether. That is a very critical thing you want to look at when designing your systems. You want to be looking out for these single points of failure. If that exists, you want to increase the redundancy by adding backups. And maybe they're passive, they're not always running, but the moment anything that is critical crashes, you have this backup that will take its place immediately. So that is load balancing strategies. In the next video, we're going to talk about another different alternative strategy that can be used or often is used in conjunction with load balancing, called clustering. So join me in the next video where we'll talk about that. Welcome back, everyone. In this video, we're going to discuss clustering, which is a very common technique in any system. It's a technique you apply onto a specific component where you increase the amount of servers that exist, but we're going to do it in a very different way than what you might be thinking. Usually this is discussed in comparison to load balancing at a high level because they serve two different functionalities, but we're going to go into how clustering actually works, but we're also going to talk about how clustering and load balancing is often used in conjunction. So looking back at load balancers, we discussed in the last video that with a load balancer, these servers act independent of one another. Each server has no idea about any other server in the system. It doesn't care. Server 1 doesn't even know that server 2 or 3 exist. Server 1 simply receives requests and then it processes them and then it moves on. It is highly independent and completely unaware of anything else around it. And this is the same is true for server 2 and the same for server 3. Now, clustering does not replace load balancing. Instead, what we need to do is we need to zero in to one of these servers. So let's take server 1 as an example. Clustering is where you have a bunch of servers that act together and are completely aware of each other and work together as a cohesive single unit towards some objective, meaning that you are essentially relying on the resources of multiple servers together in order to achieve some desired objective. So you can imagine if server 1 inside was composed of multiple other servers that are all working in conjunction. Now here, there are a couple caveats to this. The first is that each of these servers is known as nodes. You can see these nodes as, again, just a different terminology we use to capture what an independent server or a virtual machine is doing. But they're all cohesively working together. Oftentimes, these servers, even though they're different servers, you want to treat them as a singular entity. So inside of our diagram, it should be a singular server. And as a result, why they're nodes and not servers is because you want to see these 5 servers together as one server. They all respond to one IP address. They'll share one IP address. They're treated as, again, a single entity. As a result, another thing that we need to do then is you need to assign a leader node. Now, let's say we chose node 1 to be the leader. In this case, what happens is that when the requests come in, they all go through node 1. Node 1 then acts like a load balancer, and it will forward these requests evenly between the remaining nodes. But the difference between load balancers and clustering is that in load balancers, outside of this cluster example, I mentioned that none of the servers are aware of each other. Inside of this cluster, all the nodes are not only aware of each other, they're constantly communicating with each other, and they're constantly syncing their states. By syncing their states, if any one node goes down, then it's very easy for the remaining nodes to pick up the work that that one was doing. There's no latency between this, and that's the whole idea of clustering. You're trying to reduce node-to-node communication, but you're also making it extremely easy for any of the nodes to replicate the state of a node that went down. They're, again, working in conjunction towards a singular objective. And all of these nodes hold the exact same resources. They don't share resources per se, but they have the identical resources. They're identical servers. They're identical nodes. So there are a couple configurations to think about as well. As I mentioned before, when we were talking about single point of failure, we talked about redundancy. So essentially it just means that there can be passive nodes as well as active nodes. What we're seeing here is 4 nodes that are all active and sharing the load. But this might not be necessary. You may be really overutilizing resources to keep 4 nodes active if the traffic doesn't even amount to the amount required here. What we can do is maintain passive nodes. Now, nodes 4 and 5 are considered the passive nodes. They're there, but they're still syncing with nodes 3 and 2. There's still communication between those nodes. They're just not being routed the actual traffic of requests. Instead, what happens is that if nodes 3 or 2 go down, then nodes 4 and 5 will become active. So this is the whole idea around keeping these passive nodes. It's mainly more so used for resource management per se, in terms of managing your costs. But this is clustering. You can see how clustering can be used in conjunction with load balancers out in the system. Each of these servers, while in this higher level diagram, are not aware of each other. So server 1 doesn't know server 2 doesn't know server 3. Inside of the server, either server 1, server 2, or server 3, they are their own cluster of many node servers inside. Inside of the cluster, they're aware of each other. Outside of the system, amongst this high-level diagram, these servers are not aware of each other. That's load balancing and clustering. It's just a method to increase the reliability of your system. It's scaling. It's very similar to horizontal scaling, essentially. You're just increasing the amount of resources available in order to deliver on some specific objective. So that is clustering. Now that we understand clustering, let's move on with our course.
Welcome back, everyone. We are now about to begin our deep dive into databases. Now, one important thing I want to mention about databases is that inside of system design, databases contribute to a large majority of what you need to think about, because a lot of what we work about, as we've learned about throughout this course, is data. We learn about how to manipulate data. We need to think about the shape of the data, how to store the data, how to make sure the data is reliable, it comes out on time, we store it effectively. All of the things related to databases is an incredibly crucial decision-making step during the system design process. When you're architecting your system, a lot of what you're thinking about is how the data is going to flow through your architecture and flow through the system. And databases is a very critical juncture of how all that comes together. Now, luckily for us, my fantastic coworkers, Andre and Mo, have already created an extensive database and SQL course for you. So let's take a quick look at it and understand what parts of it are really crucial for our needs with system design. So here we are inside Mo and Andre's course, the Complete SQL and Databases Bootcamp. I highly recommend you go through this entire course. Databases, and specifically SQL, is a very large portion of the actual system design process. Thinking about how to work with data, where it's stored, how it's stored, and how quickly you can access that data is an incredibly crucial piece of system design, as we've already mentioned earlier in our system design section. If you are on a bit of a time crunch, or if you've already gone through this course, I still suggest you go through the whole thing, but there are key portions of this that I want to highlight that are important as far as the context of our system design course is going so far. I highly suggest you go through the history and story of data. As I mentioned, much of what we do inside of our architecture is work with data and figure out how it flows through our architecture.
So this will talk about from a high level how that works when it comes to a database. We also suggest you highly go through databases and SQL fundamentals. SQL is a very crucial type of database. It's a relational database. And a lot of our data that we're storing needs to be consistent, reliably stored, and stable. And SQL is the most stable format in order to store data. So we need to understand how SQL works and why we need it when it comes to that type of data, especially when we want to store that kind of data, why we choose SQL. It's very crucial you can recognize when designing a system whether or not you need a relational database. And then when you have that, how you're going to design your data so that it fits into that style of a relational database in the first place. It is a very crucial portion of what you do, and this is covered extensively throughout this course, but specifically it's highlighted in this section. So after you go through this section, I would suggest you go through database design. Now, database design is, again, a high-level look at how databases are structured. And it's a very good understanding of how these databases work to give you a deeper understanding of choosing a database. And this is a very crucial portion in system design. You might not work as much on the low-level implementation, but what you're going to do is you're definitely going to have to decide on what database and why. And this course right here in this section is going to cover this specific topic. So it's very important you go through this. You also should go through database landscape, performance, and security. Now, these topics on scalability, sharding, replication, backups is very crucial at a high level in order for you to integrate this into your understanding of databases as the system design portion. The reason for this is because a lot of these topics of scalability and sharding, replication, backups increases the redundancy, but specifically the reliability of our system. Remember, databases can also be a single point of failure. All of our data comes in and out of our database. So if this ever goes down, then our entire system might just not work altogether. So as a result, it's very important we make sure that it's secure, it's redundant, it's properly scaled out for levels of performance and reliability, and this all gets covered inside of this section. Not to mention, throughout this course as well, Andre and Mo both talk about system design in relation to databases because that's how crucial this topic is when it comes to system design altogether. So I highly suggest you go through this course altogether. It is a bit of a sidetrack because it's a long and extensive course, but again, when it comes to databases and when it comes to experience, you must have it. There is no way around it. So I highly, highly suggest you go through this entire course. Now, once you've gone through this course or you've gone through these key sections I've mentioned, come back to our system design course and we'll continue talking about some of the other important topics from a high level as it comes to storage and databases in system design. Another thing I want to mention about this course as well is that they do cover even more topics related to data engineering, and Redis. Redis is a flavor of database, and we use it extensively in the caching layer as we saw earlier. So this section is really great to give you a deeper understanding of how the Redis database works and how to use it. So please go through this section as well because it's crucial to the caching portion of our web architecture. Once you've done this course, you will have a good understanding of databases, and then from there, we'll circle back into the system design course and cover some additional topics that you may need to understand when it comes to this layer. So please, and I sound like a broken record at this point, go through this course. It is crucial that you have a rock solid understanding of databases, especially SQL databases, but also non-relational databases as well, which get covered in this course. Once you've done that, come back and let's continue. I'll see you in the next video after you've gone through this course. Welcome back, everyone. So hopefully you watched all of the SQL and database course. If you haven't, I'm hoping you at least watch the recommended sections, because here on out, I'm going to be referencing some of the high-level concepts that you learned throughout those sections, but also I'm going to cover a refresher of what's important and also what additional things you need to consider when thinking about system design from the context of databases. So to begin with, we want to talk about CAP theorem. Now, CAP theorem is essentially a way to think about distributed systems, particularly your databases, and what types of databases to choose for what kind of solutions that you have regarding your data. So to begin with understanding CAP theorem, we need to understand the C, A, and P stand for different things. The C stands for consistency, the A for availability, and the P for partition tolerance. Now you'll notice that there is an overlap between two of any of the three circles. The reason for this is because your system can only be two of these three things. So you can have a system that is consistent and available, you can have a system that is consistent with partition tolerance, and you can have a system that is available with partition tolerance. The thing I want to talk about, though, is that generally speaking, in almost all of your systems that are distributed, it is always going to at least have partition tolerance guaranteed. Now, we're going to talk about why you can only satisfy two of these three things, and it's really contingent on the fact in a distributed system that you have partition tolerance. Now, what is partition tolerance? So when you think about a system that is distributed, in order for it to distribute it, it implies that there are multiple nodes or duplicates of your database or your servers or your overall system. And this distribution over multiple servers throughout the world or throughout different regions is what makes it a distributed system in the first place, meaning that much of your system doesn't sit on one node. If this is the case and it's split up, then this means that by nature, you have a distributed system that communicates to each other, these nodes, through networks. Now, if they're communicating to each other through networks, that means that if at any point these communications break down because the network goes down, then you have a partition. Now, this partition is simply the fact that you have a failure in your network or a failure in the communication between servers. If this is the case, then we can think about how the fact that in almost all systems, we cannot control whether our network goes down. So this means by default in a distributed system, you have to have partition tolerance, meaning that your system must consider the fact that partitions, i.e. the breakdown of communication between two nodes, is guaranteed to be possible inside of your system. So this means that with that in mind, you must consider partition tolerance one of the absolute requirements as long as you're talking about distributed systems. So this means that if we can only have two of these three in the CAP theorem, partition tolerance is guaranteed to be one of them, again, as long as you're talking about a distributed system. Now, the next one I want to talk about is consistency. What is consistency? So again, let's imagine we have our server. Or let's more specifically talk about our database, because we're really talking about databases with CAP theorem. With our database, we might have three duplicates. If we have three duplicates, let's imagine we're talking about something that is a financial institution application, or the database handles the ability to manage the actual amount of funds in different accounts for a bank, for example. Let's say it's a banking application, and that's what our database stores, the different users inside and their respective balances. Let's imagine that each of these three ATMs connect to a different duplicate of the database or a different node containing the database data. In this case, let's imagine that we have Sarah and she goes to one of our ATMs. And let's say that when she checks the ATM for her balance, the ATM communicates with this node in the database in order to identify that her balance is $1,000. Let's say Matt, on the other hand, goes to a different ATM, and this ATM communicates with this database to see that he has a balance of 0. In this context, in order for the data to be consistent, or this database to have consistency, let's say that you look at this data that we have now collected. Sarah with her $1,000 in her balance and Matt with 0. These values are distributed across these three different databases equally, meaning that each different database must hold the same information. If Sarah were to visit any of these three ATMs, she needs to see that her balance is consistent across these three databases, meaning that she has $1,000 no matter what ATM she checks. And because no matter what ATM she checks, each of these databases that they're respectively connected to must reflect the same balance, i.e. they must hold the same data. So with this in mind, let's say Sarah performs a transaction. And the transaction she performs is that she wants to transfer $100 to Matt. So this means that her transaction has 2 steps. The first is that we must take a credit of $100 from her account and then debit $100 into Matt's account, meaning that she loses $100 and Matt gains $100. So this transaction must go into this database that it's connected to. So Sarah's $1,000 goes down to $900 and Matt's goes up to $100. Now, in order for this database to be consistent, because remember, there are 3 nodes in our system right now, so there's 3 different database nodes that all must reflect the same value. If the data is inconsistent, then if Matt were to check inside of his ATM, even though Sarah has deposited $100 into his account from her account, because this database is not consistent, he will still see that his balance is $0, even though Sarah's database that she updated has reflected that there should be $100 in there for Matt. Now, we know that this $100 does exist in the actual database where Sarah made the transaction. But because our database here is not consistent, we don't reflect that. This becomes especially problematic for a financial institution, especially if Sarah goes to another ATM and she checks that database from that ATM, and because, again, the data is inconsistent, she sees that she still has $1,000. This means that she has not actually lost the 100 according to this database node. So now, if the system was consistent, what should happen is that Sarah, when she makes that transaction, that $100 gets debited and Matt will receive the $100. So these values work. But what will happen is that no reads can happen from any of these databases unless all the other databases also get their systems updated. So all these database nodes are communicating with each other, trying to sync the state now that a transaction from Sarah has happened, meaning that Sarah's new values of 900 and Matt's value of 100 needs to be updated in every single database node. Now, if Matt were to check, well, he'll see that he has the appropriate $100 because this has reflected. And similarly, if Sarah goes to any ATM in the system, she checks her balance, she'll see that she has 900. This is what consistency means, that all of the nodes in your database must reflect the same value of all transactions that happen. Transactions are not considered complete until all the database nodes hold the same value, meaning that your data is consistent in your distributed system. Because again, a distributed system means you have multiple copies or nodes of your database, and all of them must consistently show the same data, hence consistency. So that's what consistency is. Now, if your system is consistent and partition tolerant, then you have a CP system, hence that overlap purple area there. So that is one type of system. The other one is an available system, and that's what we're going to talk about in the next video. We're going to talk about availability and what that means in the same context of databases. I'll see you in the next video. Welcome back, everyone. Let's keep talking about CAP theorem. In the last video, we discussed consistency and partition tolerance in a distributed system. Now we're going to talk about availability and what it means for a system to be available. So let's go back to our example with our database being numerous nodes, as well as representing this financial institution with ATMs and balances. Let's say inside of here, we have a partition. Remember, I mentioned that in all distributed systems, you must assume that partitions are possible, i.e. failures in the network communication between these database nodes. So here, let's imagine that this bottom right node is not able to communicate with any other database node in our system, meaning that there is a partition that has happened here. Now, let's say Sarah makes that same transaction. She wants to remove $100 from her balance and give Matt $100. What happens in our system is that this transaction completes, and let's say it is also consistent with whatever nodes that this database was able to communicate to. So that bottom left one and the one that Sarah was directly communicating to both reflect the correct data. Sarah having a new balance of $900 and Matt with $100. Now, let's say Matt is in that bottom right corner and he is connecting to the ATM that is connected to the database that is partitioned from the entire other system. Here, when he tries to check his balance, he will see that he has $0. Now, the reason why this database, regardless of being partitioned from the rest of the system, still returns $0 is because this system is available, meaning that data always gets returned regardless of whether or not a partition is detected in the system. In a system that is unavailable, if there is a partition, this database cannot guarantee that it knows for sure that the data state it has is stale or up to date with any transactions that has happened throughout the system. So if that were the case, then it would throw an error, or maybe it would tell Matt that right now the system is down. You can imagine how you might go to an ATM and the ATM tells you that the system is down. If that is the case, then that system, that ATM, and the creator of that system has decided to create a system that is not as available. Because an available system will always give you back a value, regardless of whether or not the data is stale or not. The whole idea of an available system is to always provide back data, even if the data cannot be guaranteed to be the latest and freshest data. So if your system prioritizes availability, then that's what you're doing. You are always returning back data, even if it's stale. So if you have a system that is both available and partition tolerant, then you have an AP system. So this is the CAP theorem. Essentially, you are choosing between either consistency and partition tolerance or availability and partition tolerance. Now, earlier, you do remember that I did talk about a system that is both consistent and available, a CA system. How does a CA system work? It's very simple. Essentially, a CA system is not a distributed system. You only have one central node that represents the database for your entire system. So here, any ATM all connects to one node. The reason why this is both consistent and available, or at least you can ensure that you can have both consistency and availability, is because you have no chance of partitions occurring, because there are no multiple nodes. The only way that you can have partitions is if you have a distributed system. If you have a singular node, then you are not, by definition, a distributed system, meaning that you do not even need to think about partition tolerance because partitions don't exist. So in this type of scenario, then you have a consistent and available system. So this rounds out pretty much what CAP theorem is. Now, when you choose whether you want a CP or an AP system, meaning you either get a consistent and partition tolerant system or an available and partition tolerant system, depends on the context of the problem you're trying to solve. And this decision comes down to the database you choose to use, whether you use a SQL or a NoSQL database. Now, another way to view this is where we talk about ACID and base databases, which is very similar to CAP theorem. It's the extension, and it's the same creator of the CAP theorem, or the writer of the CAP theorem, Eric Brewer, who discusses ACID and base properties of databases. And that's what we're going to cover in the next video. But before we move on, I want to make sure that you understand what CAP theorem is and what consistency, availability, and partition tolerance are in a distributed system. If any of that is unfamiliar, please rewatch these last two videos and rewatch the appropriate sections inside of that database and SQL course that we just discussed. If you're ready, let's move on to the next video where we'll discuss ACID and base properties when it comes to databases. Hello everyone and welcome back. In the last few videos, we discussed the CAP theorem when it comes to building distributed systems in relation to databases. This is an extension of those topics on CAP theorem, where we're going to talk about ACID and base properties when it comes to database selection, and it builds upon what we learned in the CAP theorem. So let's start with ACID. ACID, ACID, are 4 different properties unique to a ACID database, starting with A, which is atomic. When thinking about an atomic database, what it needs to do is it needs to ensure that these transactions are atomic. Now, what does that mean? Well, we know that with a transaction, there might be multiple records that are being modified. Maybe new records get added or deleted or updated, but the idea is that a transaction might touch multiple records in the database. In this particular case, if we were to remove $100 from Sarah's balance and then add $100 to Matt's balance, this is one transaction where we're transferring $100 from Sarah's account to Matt's account. This is one transaction, but there are two records that are being modified here. Sarah first will have to remove $100 from her balance, going down to $900. Matt, on the other hand, is another record where $100 is being added and his record updates to $100. In this case, this is what the transaction needs to do in order for it to be considered complete. But let's say that during this step, the first record, Sarah's $100, gets removed from her balance, going down to $900. But then when it's time to add the $100 to Matt's balance, the system encounters a bug, or the database encounters a bug. In this particular case, that $100 does not get added to Matt's account. What happens in order for this database to be considered atomic is it must roll back all of those values that got changed before this transaction began. So what will happen is that Sarah's $900 gets reverted back to the 1,000 as if that first step of the transaction never happened. In this case, in the event that any of these steps fail and all of the records that need to be updated don't get updated, if any of that happens, then it all rolls back as if that transaction never happened. Only if we're able to ensure that all of the appropriate records get updated in a transaction in order for it to be considered complete. If that happens and if the database guarantees that, then is this database considered atomic. So that is the A. Next is the C, which stands for consistent. We already learned about consistency. Consistency in this case is just that between every transaction, the database and all of its nodes are consistent in data, as well as all of the database is not falling victim to any bugs or any violation of the rules that govern the database, which makes it structurally sound. This means that in order for a database to be consistent, it must satisfy this value. Every transaction that happens does not compromise the structural soundness of the database itself and all of its subsequent nodes. Next, we have I, which means isolated. So in order for isolated, let's go back to talking about transactions inside of our database. Let's imagine we had two transactions that were happening around pretty much the same time. One is the Sarah account getting credited $100 and then Matt getting debited the $100 in return. The other transaction is that we want to count the total of all the accounts. And let's say inside of our database, we only have Sarah's account and Matt's account. In this case, what happens is that let's imagine that Sarah's account first subtracts the $100. So in this first step of the transaction, Sarah loses the 100 and that balance updates to 900. But let's say before the Matt debit happens, our other transaction, count total of all accounts, runs. In this particular case, the Matt balance has not updated, but it's still going to read the total of all of the accounts. And what is that total when you add it together? Well, it's $900. But in this particular case, our transaction on the left has not finished yet. So what we're doing is we are peering into all of these different accounts in the middle of a transaction. So the state where it's incomplete. And in this particular case, this $900 is incorrect because we know that Matt has yet to be debited the $100. So here, this is not isolated. In order for it to be considered isolated, what has to happen is that the count total of all accounts, regardless of when it runs, if it's running alongside this transaction on the left, it needs to count before the value actually happens, meaning that it will count when Sarah has $1,000 and Matt has 0, hence giving us the total of 1,000, or it has to happen after that transaction happens, meaning that Sarah's account gets updated to 900, Matt gets updated to 100, and then the count total runs, and it will see and add these values together, again yielding 1,000. So isolated means that the transactions are unaware of the in-between states of the other transactions. This almost makes it seem as if running all of these transactions side by side, that it happens in a sequence. This might not happen in how the database actually runs all of these transactions, but the key point here is that the transactions cannot peer into the database when another transaction is in the middle of updating the state. Isolated pretty much means that these transactions are isolated from each other. They cannot get involved in the middle of another transaction. That's isolated. And then D is durable. And durable just means that in the case that your database goes down, it does not roll back to any value if any transaction has already completed before. Meaning that if a value has been updated from a transaction, if that database goes down due to a bug or an error or whatever, it will not roll back any values to a previous value. Again, this only makes sense if those transactions are considered complete, meaning that if they're atomic, they are considered complete as well. So durable just means that the changes that get made by complete transactions persist regardless of whether or not that database goes down. Now, databases that have this ACID property are pretty much uniquely relational databases or SQL databases, which you've learned throughout that SQL course that Mo and Andre taught. If you think about a need for a database that is ACID compliant, you need a SQL database when you want these exact properties. If you don't need ACID, then you are looking for a base database. Now, base is not as pretty in the mapping of what it represents to ACID. Base stands for basically available, soft state, and eventually consistent. Now, basically available means exactly what we learned about with availability when it came to CAP theorem. It just means that if you are getting a request to a database, you always return data regardless of whether or not it's fresh or stale. Soft state is a reflection of eventual consistency. It means that the state of your data is soft or in flux. It's not hard. What this also means is because it's tied to eventual consistency is that when you think about a system that prioritizes availability, we mentioned before that maybe there's partitions or maybe there is a slowdown in actually updating all of the nodes to reflect the same state. That is not consistent because it prioritizes showing data regardless of stale or freshness of that data. But it doesn't mean that we don't want that data to become consistent at some point. Eventually consistent means exactly that. Eventually, these nodes will be consistent in the data. It's just not the priority. So as a result, our state is in a soft state because that change might happen at some point. We just don't know really when. It's not driven by the input. In an ACID-based system or database, whenever input comes in, meaning whenever a transaction occurs, the state will pause and lock until all of those nodes are up to date with the same state, which is a hard state. A soft state means that these nodes are in flux. They'll still return values. It's just that at some point they'll become consistent, but the state is in flux. So the whole way to think about base is really just that it is eventually consistent, but pretty much as available as possible as long as nodes are up. That is base properties. So a base-driven database is a NoSQL database. You might be talking about Cassandra, you might be talking about Redis, you might be talking about MongoDB. These are all NoSQL databases and they are all base compliant. So that's really it. ACID for SQL databases or relational databases, base for NoSQL databases. And that is ACID versus base. Now again, choosing an ACID or a base-based database will be dependent on what you need your data to be. If you're working with financial institutions and transactions, you're most likely always going to want a relational database because you need to prioritize consistency in your data. If you're talking about anything else like messaging apps, where you just really need the data to be available, but you don't really care whether or not that data is stale or fresh, and yeah, you might care that eventually the data is consistent, then you would pick a NoSQL database. The whole idea with availability over consistency is that this availability scales quickly and fast. Whereas you can scale relational and SQL databases, it's just a little bit more challenging because you need that consistency. And that's pretty much acid and base as well as CAP theorem when it comes to database considerations and choosing them in your system design. Welcome back, everyone. So this wraps up our System Design 101 module. In this course, we learned at a high level about all the different components that make up the majority of what you need to know when architecting a system for a web application. There's definitely a lot of low-level topics that you can go through in depth, such as the actual implementation of load balancers, whether they be with something like a reverse proxy with Nginx or using actual load balancer hardware or software. There's also numerous deeper topics that you can go into when it comes to actually implementing these systems inside of cloud infrastructure platforms such as GCP or AWS. On top of that, each of these different topics, such as coding the actual front end or the back end code that lives inside of your web servers, your databases, your servers, your queues, your job servers, etc., these all get covered by ZTM in their respective courses. As I've said before, if you've already taken that database bootcamp course on ZTM, then you have seen what it's like to do a real deep dive into databases and caching services. Again, this 101 course is meant to be a very modular small course that gives you a high-level overview of what you need to frame your learning around when it comes to these distributed services and the design of them. So hopefully you now are better equipped to go through and understand in your experience working at larger companies and working on their distributed services, what the trade-offs that you're trying to understand are and what preparation you need to know when it comes to the actual architecture of these systems. With that in mind, I do want to leave you with a list of articles of different companies and individuals who have solved unique problems inside of this kind of system design space. The reason for that is because now you have a better idea of what you're looking for and what you're reading for when they explain their experience. It's going to be a very cumulative process of building up this experience when it comes to system design decision making. Throughout this course, we've talked about the main priorities being reliability and consistency, availability. All of these topics are just designed around making the right decision for the problem you're trying to solve. There is no one-size-fits-all with system design. It's really about understanding the problem and making the correct trade-offs in the correct components, or even about where you're going to make the cuts or make the actual abstractions themselves in these different components that live in this architecture. So hopefully you have a good enough high-level understanding of what each of these represent. Of course, you can deep dive into each of them further yourself by taking more of our courses that cover these different topics that are spread throughout ZTM. And in the future, I will definitely add more modules to this course and deep dive based on the actual feedback we receive regarding what people want to learn with system design. Thank you for taking this course, and I hope to see you in the next one.
Hey there. I wanted to take a second at the end of it all, at the end of your learning journey, to just say this one thing, and that is, thank you. I know your time is valuable. We have limited time on this earth, and you decided to spend your time and your money, frankly, with us, doing something that takes a long time to learn. So truly, from the bottom of our hearts, I know it sounds cheesy, but thank you for dedicating your time and effort to this course. I hope you got what you wanted out of it, and congratulate yourself for getting this far, because a lot of people have hopes of learning, but they give up along the way. But you didn't do that. You worked through the challenges, the problems, and you got here. Now, your learning journey doesn't end here. It keeps going. But I hope this created a foundation for you to go off and learn things on your own, get a promotion, get hired, start a new business. Whatever it may be, again, thank you and best of luck with your learning journey. This is just the beginning of whatever you decide to do in the future. So thank you and good luck.